Hello there, and welcome to Science for Sleep, a place where curiosity slows its pace, ideas stretch out comfortably, and the universe is allowed to explain itself without being rushed. Wherever you are listening from tonight, whether the lights are already dimmed or you're easing gently toward a rest, I'm glad you're here. Take a moment to settle in, let your shoulders soften, and allow your attention to drift just enough that the edges of the day begin to blur. Tonight, our quiet journey begins far from anything familiar. Not at Earth, not even at the orbit of the Moon. We're starting much farther out, beyond the planets, beyond the known rhythms of our solar neighbourhood, at a place so distant and subtle that it barely announces its existence at all. A region that does not shine, does not orbit in neat circles, and does not reveal itself directly to our telescopes. It is not a planet, not a star, and not a cloud in the way we usually imagine clouds, and yet it may be the largest structure the Sun has ever claimed as its own. This is the Oort Cloud. If that name already feels vague and a little mysterious, that is fitting. The Oort Cloud is less like a clearly drawn boundary and more like a suggestion. It is the Sun's quiet influence stretched thin across space, a distant population of icy objects that drift so far away that even gravity seems to speak to them in whispers rather than commands. When people ask how big the solar system really is, they often think of the planets, or perhaps the Kuiper Belt beyond Neptune, but those are only the inner districts of a much larger domain. Before we go any further, let me ask you something simple. Where are you listening from tonight, and what time is it there, in your corner of the world? It is interesting to think that while you're here, listening to words about distant space, you're also anchored to a very local moment, a particular hour, a specific place. And yet the topic we are easing into stretches so far outward that even the idea of distance starts to feel unfamiliar. If you find this exploration calming, intriguing, or simply a pleasant companion as the day winds down, you can gently support this little pocket of quiet science by liking the video or subscribing. It helps more than you might think, and it allows this slow, unhurried way of talking about the universe to reach others who might appreciate it too. Now, let's begin to drift outward. Imagine standing somewhere far beyond the planets, so distant that the Sun no longer looks like a blazing disk, but like a bright star among many. At that distance, the warmth that once shaped worlds has faded into something barely noticeable. Light still arrives, but it has thinned, weakened, stretched across so much space that it no longer dominates the scene. The solar wind, once strong enough to carve magnetic bubbles and sculpt planetary atmospheres, has slowed and dispersed. What remains is gravity, patient and persistent, holding on to whatever still remembers where it came from. This is where the idea of the Oort Cloud begins, not as a visible structure, but as a gravitational memory, a record of the Sun's early history, preserved in countless frozen fragments that never quite escaped and never quite stayed close. These objects are not arranged in a flat disk like the planets. They are not confined to a tidy ring. Instead, they are thought to form a vast, roughly spherical halo surrounding the entire solar system. That shape alone already tells us something important. It suggests that whatever placed these objects here did not happen gently or neatly. The planets formed in a disk because they inherited the rotation of the cloud that collapsed to form the Sun. A spherical distribution hints at chaos, at gravitational nudges, at long, slow interactions with passing stars, with the galaxy itself, and with the lingering effects of the Sun's birth cluster. The question we are slowly circling tonight is not whether the Oort Cloud exists, but how far it extends. How large can something be before the word size stops being useful? When people say the Oort Cloud marks the edge of the solar system, what do they really mean? Is it a boundary, or just the place where the Sun's influence becomes difficult to notice? To appreciate the scale involved, it helps to acknowledge how limited our everyday intuition is. Even the distances between planets are already far beyond what the human mind evolved to handle comfortably. Earth and the Sun are separated by about 150 million kilometres, a distance so large that light itself takes over 8 minutes to cross it. Neptune, the most distant planet, orbits roughly 30 times farther from the Sun than Earth does, and yet even Neptune is not especially close to the edge. Beyond Neptune lies the Kuiper Belt, a region of icy bodies that includes Pluto and many similar objects. That belt extends a bit farther out, perhaps to 50 astronomical units from the Sun. An astronomical unit, just to keep our footing, is the average distance between Earth and the Sun. 50 of those already sounds enormous, but the Kuiper Belt is still part of the solar system's inner outskirts. It is closer to downtown than the suburbs. The Oort Cloud, by contrast, begins so far away that numbers start to lose their emotional impact. Estimates suggest its inner edge might start around 2,000 astronomical units from the Sun. Its outer boundary could extend to 50,000 or even 100,000 astronomical units. At that point, we are talking about distances measured not just in billions of kilometres, but in fractions of a light year. Let that settle for a moment. Reaches of the Oort Cloud may extend halfway to the nearest star. In some models, it could even overlap with the gravitational influence of other stars passing nearby over cosmic timescales. At such distances, the Sun no longer feels like the dominant presence it once was. Its gravity still holds on, but just barely. A passing star drifting a few light years away can tug on these distant objects and alter their paths. The slow, steady pull of the Milky Way itself can reshape their orbits. The Oort Cloud is less a fortress wall and more a loose gathering of travellers, all loosely bound to the same source. What makes this even more intriguing is that we have never seen the Oort Cloud directly. No telescope has captured an image of it. No spacecraft has flown through it. Everything we think we know about it comes from indirect evidence, from careful observation of comets that occasionally fall inward toward the Sun. These long-period comets arrive from all directions, not confined to the plane of the planets. Their orbits are steep, tilted, and often nearly random. That behaviour makes sense if their home is a spherical reservoir surrounding the solar system. When one of these objects is nudged, perhaps by a passing star or a subtle gravitational shift, it can begin a long, slow fall inward. After tens of thousands or even millions of years, it briefly visits the inner solar system, lights up as ice vaporizes, and then disappears again, often never to return. Each of those comets is like a message from the outskirts, a reminder that the solar system does not end neatly where the planets stop. Instead, it fades gradually into a region where definitions become soft and boundaries are hard to draw. As we move forward, we will take our time unpacking what big really means in this context. We will talk about how astronomers estimate distances they cannot measure directly, how gravity competes with the galaxy itself, and how something so vast can remain so elusive. We will also gently explore what it means to belong to a star at all, and how the Sun's influence stretches far beyond the warmth and light we feel here. For now, it is enough to sit with the idea that somewhere far beyond the familiar planets, beyond even the faint sunlight that reaches Pluto, there exists a realm of cold, quiet motion. A place where the Sun's presence is still felt, but only faintly. A reasonable place to continue is with a question that sounds simple, but becomes slippery the longer you hold it in your mind. Where exactly does the solar system end? At first glance, it feels like it should have a clean answer. After all, countries have borders, oceans have shorelines, even planets have atmospheres that eventually thin into space. Surely the solar system must have a final edge, a last marker, beyond which we can confidently say, this is no longer ours. But the moment we try to draw that line, the universe gently refuses to cooperate. If you were asked this question in school, you might have answered without hesitation. The solar system ends at Neptune. For generations, textbooks treated the outermost planet as the final stop, 8 planets orbiting the Sun in an orderly progression, and then, simply, space. That mental image is tidy, it is satisfying, it fits neatly on a classroom poster, and yet, even while Neptune quietly completes its 165-year orbit around the Sun, it is still very much embedded in a larger gravitational environment. Neptune is not perched at the edge of anything. It is just one more participant in a much wider domain. Beyond Neptune lies the Kuiper Belt, a broad disk of icy bodies extending outward for tens of astronomical units. Pluto lives there, along with countless other objects that are smaller, colder, and more distant than the classical planets. If you are feeling slightly more informed, you might say that the solar system ends at the outer edge of the Kuiper Belt. But even that answer dissolves under scrutiny. The Kuiper Belt is not a wall. It does not abruptly stop. Its population thins gradually, and beyond it, scattered objects continue to orbit the Sun on elongated paths. Some of them drift hundreds of astronomical units away before returning inward. Their orbits are stretched and tilted, influenced by gravitational nudges over billions of years. So perhaps instead, we should define the edge of the solar system by gravity itself. After all, what makes something part of the solar system? The simplest answer is this. If it is gravitationally bound to the Sun, then it belongs to the Sun. That seems logical. Gravity is the Sun's most far-reaching influence. Light fades, solar wind weakens. But gravity, though it becomes weaker with distance, never quite disappears. In theory, it extends infinitely. In practice, it competes with other gravitational forces, especially those of nearby stars and the galaxy as a whole. This is where the concept of the Oort Cloud quietly re-enters the picture. The Oort Cloud represents the farthest known region where objects are thought to remain gravitationally bound to the Sun. These icy bodies orbit at distances so extreme that a single revolution around the Sun may take millions of years. Their paths are not confined to the flat plane of the planets. Instead, they are distributed in a vast spherical shell. If gravity defines ownership, then the outer edge of the Oort Cloud might be considered the outer edge of the solar system. But even here, things become complicated. The Sun does not exist in isolation. It orbits the centre of the Milky Way, travelling through a sea of other stars, gas clouds, and dark matter. As it moves, its gravitational influence is constantly being perturbed. Passing stars, even those that drift several light-years away, can tug on distant Oort Cloud objects. The collective gravitational field of the galaxy, known as the galactic tide, subtly reshapes their orbits over time. At some distance, the gravitational pull of the Sun becomes comparable to the gravitational pull of the galaxy itself. That region is sometimes referred to as the Sun's Hill sphere, or more specifically its gravitational sphere of influence within the galaxy. Estimates suggest that this sphere may extend roughly 1 to 2 light-years from the Sun. That is astonishingly far. The nearest star system, Alpha Centauri, lies about 4.37 light-years away. So the Sun's gravitational dominance may stretch nearly halfway to the nearest star. Notice the word dominance, not ownership, not exclusivity. Dominance implies competition. It means that beyond a certain distance, the Sun is no longer the primary gravitational authority. Instead, objects are influenced as much by the galaxy as by the Sun. So if we define the solar system as everything gravitationally bound to the Sun, then the edge might lie somewhere near the outermost reach of this gravitational sphere. And that is roughly where scientists believe the outer Oort Cloud resides. Yet there is another possible boundary, and this one has already been crossed by human technology. You may have heard of the heliosphere. This is the enormous bubble carved out by the solar wind, the steady stream of charged particles flowing outward from the Sun. As the solar wind expands in all directions, it pushes against the interstellar medium, the thin gas and plasma that fill the galaxy. The boundary where the solar wind slows down and begins to mix with interstellar material is called the heliopause. Beyond that point, the Sun's magnetic influence is no longer dominant. Instead, interstellar space takes over. In 2012, the Voyager 1 spacecraft crossed the heliopause. Voyager 2 followed in 2018. These spacecraft are now travelling through interstellar space. By that definition, they have left the Sun's magnetic bubble. Does that mean they have left the solar system? The answer depends entirely on how we choose to define it. If the solar system is defined by the heliosphere, then yes, Voyager has exited it. If the solar system is defined by gravitational binding to the Sun, then no, Voyager is still very much within it. Even now, gravity from the Sun continues to shape its trajectory, however slightly. This illustrates something important. The solar system does not have a single edge. It has layers of influence, each fading at a different distance. First, there is the region dominated by planetary orbits. Then, the Kuiper Belt. Then, the scattered disk. Far beyond that, the hypothetical inner Oort Cloud, followed by the much larger outer Oort Cloud. Meanwhile, the heliosphere forms a magnetic boundary much closer in. And beyond all of these lies the gradual blending of the Sun's gravity with that of the Milky Way. Instead of a line, we have a gradient. If you imagine the Sun as a campfire, then the planets sit comfortably within the circle of bright light. The Kuiper Belt lies in the dimmer glow. The Oort Cloud drifts in the faintest suggestion of warmth, where the fire is still present, but only just. Eventually, the light becomes indistinguishable from the background night. It is tempting to want a precise answer, a number, a clear distance at which we can place a marker and say, here, this is the end. But nature rarely arranges itself for our convenience. Astronomers sometimes estimate that the outer edge of the Oort Cloud may lie around 100,000 astronomical units from the Sun. That is roughly 1.6 light years. At that distance, the Sun's gravity is incredibly weak. A gentle gravitational nudge from a passing star could easily unbind an object and send it drifting into interstellar space. In fact, this likely happens from time to time. The Oort Cloud is not a permanent structure in the way a planet is permanent. It is a dynamic population. Objects can be lost. Others may be captured. Over billions of years, the composition of the cloud slowly evolves. This raises another subtle question. If the Sun can capture objects from interstellar space and lose objects to it, then where does ownership truly lie? If an icy body drifts into the Sun's gravitational influence and becomes bound, does it instantly become part of the solar system? And if one drifts away, does it cease to belong? These are not just philosophical curiosities, they are practical considerations in celestial mechanics. The boundary of the solar system, in gravitational terms, is defined by a balance of forces, and balance points are not sharp edges, they are zones of transition. Even the nearest stars have similar extended clouds of debris. It is possible that the outer edges of our Oort Cloud occasionally overlap with the outer edges of another star's gravitational reach, especially when stars pass relatively close to one another over cosmic timescales. In that sense, the solar system is less like an island and more like a region in a vast archipelago, with boundaries that shift slowly over millions of years. As we continue to stretch our understanding outward, it becomes clear that the idea of an end may not be the most useful way to think about it. Instead, perhaps we should ask where the Sun's influence becomes negligible, where its pull is no longer the primary force shaping motion, and even that depends on perspective. From the standpoint of planetary formation, the meaningful solar system ends well within the Kuiper Belt. That is where the building blocks of planets formed and evolved. From the standpoint of long-period comets, the solar system extends deep into the Oort Cloud. From the standpoint of magnetic influence, it ends at the heliopause. From the standpoint of galactic dynamics, it fades gradually into the gravitational background of the Milky Way. All of these answers are correct. None of them are complete. Perhaps the better question is not, where does the solar system end, but which influence are we measuring? Light, wind, gravity, or formation history? Each draws its own boundary, Let your mind sit with the idea that the solar system is not a tidy bubble with a sharp shell. It is a layered structure with overlapping zones of influence that grow fainter with distance. The Oort Cloud occupies the outermost of these zones, where the sun's grip is weakest, but not yet gone. If we're going to understand how large the Oort Cloud might be, it helps to begin with something more grounded, something we can actually observe. Before we try to measure a distant, invisible shell of icy bodies, we should first ask a simpler question. What are the farthest things we have ever truly seen? That question may sound straightforward, but the answer depends very much on what we mean by seen. Are we talking about objects our eyes can detect, objects photographed by telescopes, or objects whose presence we infer from subtle movements and faint signals? Astronomy is full of layers like that. Sometimes we see directly, other times we see through consequences. Let's start close to home. The most distant object visible to the unaided human eye is not especially far on a cosmic scale. Under very dark skies, you can see the Andromeda Galaxy. It appears as a faint smudge, and most people who spot it might not even realize what they are looking at. That smudge is about 2.5 million light-years away. In other words, the light entering your eyes left Andromeda long before human civilization existed in its present form. But that kind of distance, measured in millions of light-years, belongs to a different category of astronomy. Those are galaxies. They are not part of our solar system. They are not even part of our immediate stellar neighbourhood. When we talk about the edge of the solar system, we're talking about something far smaller, even though it will still stretch our imagination. So let's narrow the scope. Within our own solar system, the farthest confirmed objects we have directly imaged are distant trans-Neptunian objects in the Kuiper Belt and beyond. Some of these bodies orbit at distances of over 100 astronomical units from the Sun. That is already more than 3 times farther out than Pluto's average orbit. To put that in perspective, remember that 1 astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. Neptune orbits at around 30 astronomical units. Pluto's orbit averages around 39 astronomical units. When we start talking about objects at 100 astronomical units, we are already deep into the outer solar system, and yet even 100 astronomical units is still nowhere near the inner edge of the Oort Cloud, which may begin around 2,000 astronomical units away. That difference is not small, it is enormous. Consider Voyager 1, the farthest human-made object from Earth. Launched in 1977, it has been travelling outward for nearly half a century. As of now, it is roughly 160 astronomical units from the Sun. That is farther than any spacecraft has ever gone. It has crossed the heliopause. It is officially in interstellar space, at least in terms of solar wind influence. And yet, Voyager 1 is still much closer to the Sun than the estimated inner boundary of the Oort Cloud. If the inner Oort Cloud begins around 2,000 astronomical units, then Voyager has not even reached 1/10 of the distance required to arrive there. At its current speed, it would take thousands of years to travel that far. This gives us an important grounding point. The farthest human object ever sent into space has barely scratched the outermost layers of the Sun's gravitational domain. Now, let's think about the farthest natural objects we have detected that still orbit our Sun. There are objects like Sedna, a distant icy world discovered in 2003. Sedna's orbit carries it out to roughly 900 astronomical units at its farthest point. That is extraordinary. At its closest approach, it comes within about 76 astronomical units of the Sun, but most of its orbit lies far beyond the Kuiper Belt. Sedna is not alone. A handful of similar objects have been discovered with extremely elongated orbits that take them hundreds of astronomical units away. These bodies are often referred to as detached objects, because their orbits are not strongly influenced by Neptune or the other giant planets. Some astronomers suspect that these objects may belong to the inner Oort Cloud, sometimes called the Hills Cloud. If that is true, then Sedna and its cousins might be the closest representatives of the vast structure we're trying to understand. But even Sedna, impressive as it is, does not come close to the outer reaches of the Oort Cloud. This is where our sense of scale begins to stretch. The outer Oort Cloud may extend tens of thousands of astronomical units from the Sun. Some estimates suggest it could reach 50,000 astronomical units. Others suggest it may extend as far as 100,000 astronomical units. At 100,000 astronomical units, you're about 1.6 light-years from the Sun. Let's pause with that number. The nearest star system, Alpha Centauri, lies about 4.37 light-years away. So if the Oort Cloud extends to 1.6 light-years, then it stretches more than a third of the way to the nearest star. That means the farthest natural objects that are still gravitationally bound to our Sun may be drifting through space at distances where nearby stars exert comparable gravitational influence. Now, here is the crucial point. We have never seen one of these outer Oort Cloud objects directly. Not one. They are too small, too dark, and too distant. At those distances, even a large icy body reflects almost no sunlight back toward Earth. Our telescopes, powerful as they are, cannot detect individual Oort Cloud objects in their distant orbits. Instead, we detect them only when they are disturbed. Long-period comets provide the evidence. These are comets with orbital periods of tens of thousands or even millions of years. They arrive from all directions in the sky, not confined to the flat plane of the planets. Their trajectories suggest that they originate in a roughly spherical reservoir surrounding the solar system. When one of these comets is nudged by a passing star or by the slow, gravitational influence of the Milky Way, its orbit can shift. It may begin a long inward journey toward the Sun. As it approaches, solar heat vaporizes its ices, creating the glowing coma and tail we associate with comets. For a brief period, perhaps a few months or years, it becomes visible to telescopes. Then it swings back out into darkness, often not to return for hundreds of thousands of years. Each long-period comet is a messenger from the outskirts. It tells us that something vast and distant exists, even if we cannot see it directly. So when we ask about the farthest things we have ever seen, we must separate two categories. First, there are the farthest things we have directly imaged within the solar system. These include distant Kuiper Belt objects and a few detached objects like Sedna. These are located hundreds of astronomical units away. Second, there are the farthest objects whose existence we infer through gravitational evidence. These are the icy bodies of the Oort Cloud, stretching tens of thousands of astronomical units from the Sun. In terms of direct observation, our reach is still very limited. In terms of indirect inference, our understanding extends far beyond our cameras. This distinction is important. It reminds us that astronomy often works like detective work. We do not need to see every object to know that it exists. We can study the motions of comets, calculate their orbits backward in time, and determine that they likely originated from a distant spherical distribution. From those calculations, we can estimate how large that distribution must be. Another interesting comparison comes from looking beyond our solar system. Astronomers have observed debris disks around other stars. These disks are composed of dust and icy bodies, somewhat similar to our Kuiper Belt. In some cases, these disks appear to extend hundreds of astronomical units from their host stars. However, even with modern telescopes, we cannot directly observe Oort Cloud-like structures around other stars. If they exist, they are simply too faint and too extended to detect easily. That means our own Oort Cloud, if it exists as theorized, may be one of the largest structures associated with any star, and yet it remains invisible even to us. Returning to human-made exploration, it is humbling to realize how small our footprint still is. Voyager 1 and Voyager 2 are traveling outward at about 17 kilometers per second. That sounds fast, and by human standards it certainly is. But at that speed, reaching even 1,000 astronomical units would take many centuries. Reaching the inner edge of the Oort Cloud at 2,000 astronomical units would take thousands of years. Reaching the outer edge at tens of thousands of astronomical units would take tens of thousands of years. No spacecraft currently planned or conceived could traverse the entire Oort Cloud within a human lifetime. So when we talk about the farthest things we have ever seen, we must acknowledge that the Oort Cloud represents a frontier beyond direct exploration. The farthest confirmed solar system object we have directly observed is still less than 1/10 of the distance to the inner Oort Cloud. The farthest human-made object has not yet approached that region. And yet, gravitational evidence strongly suggests that a vast population of icy bodies occupies that space. In a way, this situation is similar to early ocean exploration. Sailors once knew that land existed beyond the horizon because of indirect signs, currents, birds, drifting vegetation. They did not see the distant continent, but they inferred it. We are in a similar position with the Oort Cloud. We have not seen it directly. But the comets arriving from every direction serve as our drifting clues. What is the region like just beyond Neptune, where objects transition from the relatively structured disk of the Kuiper Belt into more scattered, elongated orbits? Neptune does not sit at the edge of anything dramatic. There is no cliff in space, no sharp drop, no sudden darkness. Instead, as you move outward past the orbit of the 8th planet, the solar system simply becomes quieter. The sunlight grows weaker, the intervals between objects grow wider. The familiar pattern of major planets gives way to a sparse and scattered landscape. This region, just beyond Neptune, is often treated as an afterthought in casual discussions of astronomy. And yet it is the beginning of the solar system's true outer territory. If we want to understand how something as vast as the Oort Cloud could exist, we first need to pass through this transitional zone, where the architecture of the solar system begins to loosen. Neptune orbits the Sun at an average distance of about 30 astronomical units. Even at that range, the Sun still shines brightly, though only about 1/900th, as intense as it does at Earth. Neptune is cold, certainly, but it is not in total darkness. It remains firmly within the Sun's central domain. Once you travel beyond Neptune, however, you enter the Kuiper Belt. This region is not empty. It contains millions of icy bodies, remnants of the early solar system that never coalesced into a full-size planet. Pluto is the most famous of them, but it is only one among many. The Kuiper Belt extends roughly from about 30 astronomical units to perhaps 50 astronomical units from the Sun. Within this span, objects orbit in a relatively flat disk, similar to the planets, because they formed from the same rotating cloud of gas and dust that gave birth to the Sun. But even within the Kuiper Belt there is variation. Some objects follow nearly circular orbits, others are caught in resonances with Neptune, meaning their orbital periods are linked in precise ratios. Pluto, for example, completes 2 orbits around the Sun for every 3 orbits of Neptune. That resonance keeps it gravitationally stable despite its crossing path. As you continue outward, the Kuiper Belt thins, objects become less frequent, their orbits grow more elongated. This is where we begin to encounter what astronomers call the scattered disk. This scattered disk is a population of icy bodies with highly eccentric and often tilted orbits. Many of these objects were likely flung outward by gravitational interactions with the giant planets, especially Neptune, during the early history of the solar system. Instead of settling into stable circular paths, they were tossed onto stretched trajectories that carry them far from the Sun before looping back inward. Sedna, which we mentioned earlier, is sometimes grouped with these distant objects, though its orbit is so extreme that it may represent something slightly different. Its path suggests it is no longer strongly influenced by Neptune. Instead, its motion hints at the gravitational imprint of the solar system's earliest environment, perhaps even interactions with other stars when the Sun was young and part of a dense stellar cluster. What is important here is that the region beyond Neptune is not a clean transition from planetary system to Oort Cloud. It is layered and gradual. Between 50 and 100 astronomical units, we move through the outer Kuiper Belt and into increasingly scattered populations. Between 100 and several hundred astronomical units, we find detached objects whose orbits are influenced less by the known planets and more by distant gravitational effects. This zone is sometimes called the extended scattered disk. It represents a kind of buffer region between the structured inner solar system and the distant spherical Oort Cloud. If you were travelling outward from the Sun, this region would feel different from the planetary zone. There would be no large planets looming nearby. The nearest substantial body might be hundreds of millions of kilometres away. The gravitational pull of Neptune would still be present, but much weaker. Sunlight at 100 astronomical units is about 10,000 times fainter than it is at Earth. The Sun would appear as an extremely bright star, but no longer as a dominating disk. Its warmth would be negligible. Temperatures would hover just a few dozen degrees above absolute zero, and yet, even here, you are nowhere near the Oort Cloud. This is one of the most surprising aspects of the solar system structure. The region that feels incredibly distant to us, beyond Neptune and even beyond the Kuiper Belt, is still relatively close compared to the vast halo that may surround everything. If the inner Oort Cloud begins around 2,000 astronomical units, then everything within the first few hundred astronomical units is essentially still part of the inner frontier. Let's pause with that comparison. From Earth to Neptune, about 30 astronomical units. From Neptune to the outer edge of the Kuiper Belt, perhaps another 20 astronomical units. From there to 100 astronomical units, a doubling of distance again, and yet, from 100 astronomical units to 2,000 astronomical units is another leap 20 times larger. The quiet frontier beyond Neptune is therefore not the outer boundary of the solar system. It is more like a long approach road leading towards something much more expansive. This transitional region also tells us something about how the Oort Cloud may have formed. In the early solar system, the giant planets were not necessarily in the positions they occupy today. Models of planetary formation suggest that Jupiter, Saturn, Uranus, and Neptune migrated over time. As they shifted, they scattered countless icy bodies outward. Some of those objects were flung completely free of the Sun's gravity and became interstellar wanderers. Others were placed on elongated orbits that extended thousands of astronomical units from the Sun. Over time, passing stars and the gravitational pull of the Milky Way itself altered those orbits further. Instead of remaining in a flat disk, the distant objects were gradually reshaped into a spherical distribution. In that sense, the quiet frontier beyond Neptune is like the launching ground of the Oort Cloud. It is where the scattering began. It is the region where gravitational interactions stretch the solar system outward. Even today, this region remains dynamically active. Objects in the scattered disk can still be perturbed. Some may eventually be nudged inward, becoming short-period comets. Others may be nudged outward, contributing to the distant reservoir. It is also worth noting that this frontier is where discussions of hypothetical objects often arise. The idea of Planet 9, for instance, emerged from observations of unusual clustering in the orbits of some distant trans-Neptunian objects. While Planet 9 has not been confirmed, the fact that such a hypothesis can exist reminds us how little we have directly observed in this region. The distances involved make detection difficult. Objects reflect very little sunlight. Their motion across the sky is slow. Large surveys are required to detect even relatively large bodies. This means that the region beyond Neptune is still being mapped. New objects are discovered regularly. Each discovery refines our understanding of the solar system's structure. But even as we push the boundary of observation outward, the Oort Cloud remains beyond direct reach. If we imagine the solar system as a city, then the planets are the busy downtown core. The Kuiper Belt is the outer suburbs, the scattered disk is the rural outskirts, and the Oort Cloud is a vast countryside extending far beyond, where homes are so widely spaced that neighbours may be separated by enormous distances. Yet all of it, from Mercury's orbit to the farthest icy body, is connected by gravity to the same star. The quiet frontier beyond Neptune teaches us something essential about scale. It shows that distance in space does not increase in gentle increments. It grows exponentially. Each new region we explore is not just a little farther out, but vastly more expansive than the last. It can be tempting to think of the Kuiper Belt as the final organised structure of the solar system, a broad ring of icy debris beyond Neptune where the last recognisable patterns still hold together. Compared to the vast emptiness beyond, the Kuiper Belt feels almost familiar. Objects orbit in roughly the same plane as the planets. Their motions are predictable. Their distances, while extreme, are still within a range that astronomers can observe directly with modern telescopes. But the Kuiper Belt is not the end of the story. It is more like a threshold. And beyond that threshold lies something related yet fundamentally different. Something that shares the same raw materials, the same icy origins, but exists on a scale that dwarfs the Kuiper Belt entirely. This is where the Oort Cloud earns its reputation as the Kuiper Belt's distant cousin. The connection between the two is not immediately obvious if you only look at their locations. The Kuiper Belt is a flattened disk, extending from about 30 to roughly 50 astronomical units from the Sun, with some scattered members reaching farther. The Oort Cloud, by contrast, is thought to form a vast spherical shell beginning thousands of astronomical units away and extending tens of thousands more. One is relatively compact and structured. The other is diffuse and enormous, and yet they are linked by origin. Both the Kuiper Belt and the Oort Cloud are made primarily of icy remnants from the early solar system. These are bodies composed of water ice, frozen gases like methane and ammonia, and rocky material. They are leftovers from planet formation, pieces that never became part of a full-size planet. Early in the solar system's history, the region beyond the forming giant planets was filled with such material. There was far more mass than we see today. Over time, gravitational interactions reshaped that population dramatically. The Kuiper Belt represents the portion of that material that remained relatively close to the plane of the planets and avoided being flung too far outward. Its members are survivors of a chaotic youth, but they are survivors that stayed within a few dozen astronomical units of the Sun. The Oort Cloud, on the other hand, is thought to contain the objects that were scattered much more violently. When the giant planets formed, especially Jupiter and Saturn, their immense gravity acted like a gravitational slingshot. As icy bodies passed near these planets, they could gain or lose energy. Some were sent inward, others were ejected from the solar system entirely, and a significant fraction were flung outward onto extremely elongated orbits. At first, these scattered objects likely followed paths that still lay close to the plane of the planets, but over time, other forces came into play. Passing stars, the slow pull of the Milky Way's gravity, and the cumulative effect of billions of years of subtle perturbations gradually altered those orbits. The result was a transformation. What began as a flattened disk of debris slowly evolved into a roughly spherical distribution. Orbits tilted, paths randomized. The memory of the original plane faded. In that sense, the Oort Cloud can be thought of as the Kuiper Belt's distant cousin not only because of shared composition, but because of shared ancestry. They are siblings separated by circumstance. One stayed relatively close, shaped primarily by the gravity of the Sun and the outer planets. The other was cast far outward and reshaped by influences beyond the solar system itself. This relationship helps explain one of the most important differences between the two regions: directionality. Objects in the Kuiper Belt orbit in roughly the same direction and plane as the planets. Their motion reflects the rotation of the original protoplanetary disk from which the solar system formed. Objects from the Oort Cloud, by contrast, arrive from all directions. Long-period comets appear in the sky at any inclination. Some plunge in from above the plane of the planets, others arrive from below. This isotropic distribution is one of the strongest pieces of evidence for the Oort Cloud's spherical shape. It is also what distinguishes Oort Cloud comets from short-period comets, which typically originate in the Kuiper Belt and follow orbits closer to the planetary plane. So while the Kuiper Belt and the Oort Cloud share material and history, their present-day behaviour reflects very different dynamical environments. Another way to appreciate their relationship is through scale. The Kuiper Belt is large by human standards. Its width alone spans billions of kilometres, and yet, compared to the Oort Cloud, it is a small inner feature. If the Kuiper Belt extended out to 50 astronomical units, then the inner edge of the Oort Cloud may begin at around 2,000 astronomical units. That is 40 times farther out. The outer edge of the Oort Cloud could lie at 50,000 astronomical units or more. That is 1,000 times farther than the Kuiper Belt's outer boundary. Imagine a map where the Kuiper Belt is a thin ring just beyond the planets, while the Oort Cloud is a faint haze stretching nearly halfway to the nearest star. The difference is not just one of distance, but of volume. The volume enclosed by a spherical shell increases dramatically with radius. Even if the Oort Cloud is extremely sparse, containing objects separated by enormous distances, the sheer size of the region means it could hold an immense number of bodies. Some estimates suggest the Oort Cloud may contain trillions of icy objects. Others propose numbers in the hundreds of billions. Either way, it likely outweighs the Kuiper Belt in total population by a wide margin. And yet, because its members are so widely dispersed, the Oort Cloud feels emptier. The Kuiper Belt, though smaller, is denser. Objects there are closer together. Interactions are more frequent. Observations are easier. This contrast often leads to confusion. People sometimes imagine the Oort Cloud as a dense swarm of objects, like a fog of ice surrounding the Sun. In reality, it is more like a vast and nearly empty volume, where individual objects are separated by distances comparable to the distance between planets. If you were somehow placed inside the Oort Cloud, you might not see anything at all. The nearest object could be millions of kilometres away. There would be no glowing ring, no visible boundary, just darkness, punctuated by distant stars. This invisibility is part of what makes the Oort Cloud so challenging to study. Astronomers cannot point a telescope and photograph it. Instead, they rely on statistical evidence. They analyse the distribution of long-period comet orbits. They model how objects would behave under the influence of passing stars and galactic tides. They test whether those models match what we observe. The Kuiper Belt, by contrast, can be surveyed directly. Large telescopes scan the sky, detect faint moving points of light, and track their orbits over time. This direct observation has allowed astronomers to classify Kuiper Belt objects into different populations and resonances. No such detailed map exists for the Oort Cloud. That difference in observability reinforces the sense that the Kuiper Belt is familiar territory, while the Oort Cloud remains hypothetical. But hypothetical does not mean speculative. The evidence for the Oort Cloud is strong, even if indirect. In fact, the relationship between the Kuiper Belt and the Oort Cloud helps strengthen the case for the latter's existence. We already know that the early solar system was capable of scattering objects outward. We already see a population of distant, detached bodies like Sedna that occupy intermediate orbits. We already observe comets arriving from a spherical distribution. All of these facts fit naturally into a picture where the Kuiper Belt and the Oort Cloud are part of a continuous story rather than isolated features. Another interesting connection between the two regions lies in their vulnerability. Kuiper Belt objects are influenced primarily by the Sun and the giant planets. Their orbits can be altered by resonances and close encounters, but the overall structure of the belt is relatively stable on long timescales. Oort Cloud objects, by contrast, exist in a more precarious balance. Their binding to the Sun is weak. A passing star, even one several light-years away, can perturb their orbits. The slow gravitational pull of the Milky Way can gradually change their trajectories. This makes the Oort Cloud a dynamic, evolving structure. Objects can be stripped away, others can be nudged inward. Over billions of years, the cloud slowly loses members. At the same time, it may also gain new ones. It is possible that the Sun occasionally captures interstellar objects that pass nearby at low relative speeds. Some of these may become loosely bound and join the outer reaches of the Oort Cloud. If so, the Oort Cloud would not be composed exclusively of native solar system material. It would be a mixed population, containing both ancient solar debris and visitors from other star systems. The Kuiper Belt, by contrast, is almost certainly composed entirely of material that formed within the solar system. This distinction matters because it highlights the Oort Cloud's role as a boundary region, not just spatially, but dynamically. It is where the solar system interacts with the broader galaxy. It is where the Sun's influence blends into the background gravitational field of the Milky Way. In that sense, calling the Oort Cloud the Kuiper Belt's distant cousin is more than a poetic analogy. It captures a real evolutionary relationship. Both regions formed from the same original population of icy bodies. Both preserve clues about the solar system's early history, but they diverge dramatically in their subsequent evolution. One remained close and structured. The other was cast outward and reshaped by forces far beyond the planets. How did astronomers first suspect that a spherical halo of icy bodies existed at all? What clues led them to propose something so immense even before they could see it? Long before anyone spoke confidently about a vast spherical halo surrounding the Sun, astronomers were puzzled by something much smaller and far more dramatic: comets. Comets have a way of capturing attention. They appear suddenly, grow bright, stretch luminous tails across the sky, and then vanish again into darkness. For most of human history, they were treated as omens or unpredictable visitors. It was only with the development of precise telescopic observations and orbital calculations that their motions began to make sense. By the early 20th century, astronomers had already determined that many comets follow highly elongated orbits around the Sun. Some return every few decades. Halley's Comet, for instance, has an orbital period of about 76 years. These shorter period comets generally travel in orbits that lie near the plane of the planets, suggesting that they originate from a flattened disk-like region. But there was another category that did not fit so neatly into that pattern. These were the long-period comets. Their orbits are stretched almost to the breaking point. Some take tens of thousands of years to complete a single journey around the Sun. Others may require millions of years, and unlike the short-period comets, they arrive from all directions. That detail turned out to be crucial. If you map the inclinations of long-period comets, you do not see a concentration near the plane of the planets. Instead, their orbits appear randomly oriented. Some dive in from above the solar system, others approach from below. Their paths form a roughly spherical distribution around the Sun. By the mid-20th century, this pattern demanded explanation. Enter Jan Oort. Jan Oort was a Dutch astronomer, born in 1900, whose work spanned many areas of astronomy. He is perhaps best known for contributions to galactic structure, but in 1950 he turned his attention to the puzzling behaviour of long-period comets. At that time, astronomers had compiled enough cometary orbits to begin searching for patterns. Oort noticed something curious. When he calculated the original orbits of long-period comets, adjusting for the gravitational influence of the planets, he found that many of them had extremely large semi-major axes. In other words, their average distances from the Sun were enormous. More intriguingly, many appeared to be arriving on orbits that were only barely bound to the Sun. Their orbital energies suggested that they originated from very far away, from a reservoir so distant that the Sun's gravitational hold was extremely weak. This led Oort to a bold proposal. He suggested that there must exist a vast cloud of icy bodies surrounding the solar system at distances of tens of thousands of astronomical units. From time to time, gravitational disturbances would nudge some of these bodies inward, sending them toward the Sun where they would become visible as long-period comets. This hypothetical structure would explain several key observations at once. First, it would account for the nearly spherical distribution of cometary inclinations. If comets originate in a spherical cloud, then they would approach the Sun from all directions. Second, it would explain why so many long-period comets appear to be making their first visit to the inner solar system. If they originate from a distant reservoir, they could remain undisturbed for millions or billions of years before being perturbed inward. Third, it would explain why comets seem to fade or disappear after repeated passes near the Sun. Once a comet enters the inner solar system, gravitational interactions with the planets can alter its orbit. Some are ejected entirely, others are captured into shorter period orbits. Over time, the reservoir of new comets would need to be replenished from afar. Oort's reasoning was careful and grounded in orbital mechanics. He did not claim to see the cloud. He inferred its existence from the statistical distribution of cometary orbits. It is worth appreciating how indirect this conclusion was. Imagine standing in a dark room and occasionally seeing a single firefly drift past your face. You never see the rest of the swarm. You only see individuals passing briefly through a small illuminated space. From that limited evidence, you attempt to infer the existence of a vast unseen population beyond the light. That is essentially what Oort did. He examined the orbits of comets that happened to pass through the inner solar system and asked where they must have come from. The answer pointed consistently to a distant spherical reservoir. Of course, proposing such a structure raised further questions. How did it form? Why did it take on a spherical shape? And how large might it be? Oort estimated that the cloud might extend up to about 100,000 astronomical units from the Sun. That figure was not precise. It was an order of magnitude estimate based on the energies of observed comets. At 100,000 astronomical units, the distance corresponds to about 1.6 light years. That places the outer edge of the cloud nearly halfway to the nearest star. To suggest that the Sun's gravitational domain might extend that far was a dramatic shift in perspective. Until then, many people casually thought of the solar system as ending somewhere beyond the outer planets. Oort's proposal implied that the Sun commands a region of space far larger than previously imagined. There were, and still are, uncertainties in this model. For example, if the Oort Cloud exists, why do we not observe more comets than we do? The answer lies in the weakness of gravitational perturbations. Only a tiny fraction of Oort Cloud objects are nudged inward at any given time. Most remain in distant, stable orbits for eons. Another challenge concerns the total mass of the cloud. Early estimates suggested it might contain enough material to account for the observed comet flux, but later models refined these numbers. The current consensus is that the Oort Cloud may contain trillions of icy bodies, with a total mass perhaps a few times that of Earth. Even so, spread over such a vast volume, it would be incredibly sparse. Oort also recognised that the cloud's existence implied an early period of intense scattering. The giant planets must have ejected vast numbers of icy planetesimals outward. Some would have escaped entirely. Others would have been placed into distant, loosely bound orbits. Subsequent research expanded on this idea. Astronomers proposed that the Sun likely formed in a stellar cluster, surrounded by other young stars. In such an environment, close stellar encounters would have been more common. These encounters could have helped reshape the orbits of scattered planetesimals, transforming an initially flattened distribution into a spherical cloud. In that sense, the Oort Cloud is not merely a collection of debris. It is a fossil record of the solar system's earliest environment. Its structure may preserve information about how crowded the Sun's birth cluster was, how frequently stars passed nearby, and how violently the giant planets migrated. Jan Oort's original paper did not answer all of these questions. It simply provided a compelling framework that tied together the mystery of long-period comets. Over the decades, that framework has been refined, challenged, and strengthened. Numerical simulations of planetary formation now routinely produce distant clouds of icy bodies when giant planets scatter planetesimals outward. Observations of exoplanetary systems suggest that such scattering may be common. Yet despite decades of research, no telescope has ever imaged the Oort Cloud directly. its existence remains inferred rather than observed. That fact makes Oort's insight all the more impressive. From a set of orbital calculations and statistical patterns, he proposed one of the largest known structures associated with any star. He effectively expanded the scale of the solar system by orders of magnitude, using nothing more than careful reasoning and the paths of icy visitors. When we talk about how big the Oort Cloud really is, we are building on that foundation. We are taking the faint hints provided by long-period comets and asking how far outward the Sun's gravitational reach might extend. We are considering the delicate balance between solar gravity, passing stars, and the Milky Way's tidal forces. If it is indeed spherical, how spherical is it? Is there an inner region distinct from an outer one? How sharply defined is its boundary? By the time we reach the idea of a vast spherical cloud surrounding the Sun, it is easy to let the word cloud mislead us. The mind may picture something soft and dense, perhaps like a mist or a halo glowing faintly in starlight. But the Oort Cloud, if it exists as astronomers describe it, is nothing like that. It is not thick. It is not luminous. It does not resemble a ring or a band you could see from afar. It is instead an immense volume of space containing scattered fragments of ice and rock, each separated by distances so large that emptiness dominates. When scientists describe the Oort Cloud as spherical, they are not imagining a solid shell. They are describing the statistical distribution of orbits. Long-period comets approach the Sun from every direction. Their inclinations are random. Some plunge inward from far above the planetary plane, others arrive from below. That randomness implies a roughly spherical source. The Kuiper Belt, by contrast, is flat because it reflects the rotating disk from which the planets formed. The Oort Cloud does not preserve that flatness. Its members have had billions of years to be nudged and tilted by passing stars and by the slow gravitational pull of the Milky Way. Over immense stretches of time, those perturbations erased much of the original alignment. To understand how large this sphere might be, we need to be precise with numbers, even if those numbers stretch beyond everyday comprehension. The inner Oort Cloud is thought to begin somewhere around 2,000 astronomical units from the Sun. That is about 300 billion kilometers. Light from the Sun takes roughly 11 days to travel that far. Already, we are well beyond any region directly explored by spacecraft. The outer Oort Cloud may extend to 50,000 astronomical units, and possibly as far as 100,000 astronomical units. At 100,000 astronomical units, we are about 1.6 light-years from the Sun. The nearest star system, Alpha Centauri, is about 4.37 light-years away. So if the outer estimates are correct, the Oort Cloud could stretch more than 1/3 of the way toward our nearest stellar neighbour. It's important to pause here and consider what that means geometrically. A sphere with a radius of 50,000 astronomical units encloses a volume vastly larger than a sphere with a radius of 50 astronomical units. Volume increases with the cube of the radius. If you multiply the radius by 1,000, you multiply the volume by 1 billion. The Kuiper Belt may extend to roughly 50 astronomical units. The outer Oort Cloud may extend 1,000 times farther than that. In terms of volume, the Oort Cloud's outer reaches could encompass roughly 1 billion times more space than the region within the Kuiper Belt. And yet, despite that enormous volume, the density of material within the Oort Cloud is extremely low. Astronomers estimate that the Oort Cloud may contain trillions of icy bodies. Some may be a few kilometers across, others may be smaller. A handful could be larger, perhaps comparable to small moons. But even if the number reaches into the trillions, those objects are spread across a sphere with a diameter of up to 200,000 astronomical units. If you were positioned somewhere within the outer Oort Cloud, the nearest object might be millions or tens of millions of kilometers away. There would be no visible clustering, no dramatic scenery, just isolated bodies drifting in extremely long, slow orbits. Each object follows its own elongated path around the Sun. At those distances, orbital periods are immense. A single revolution could take millions of years. In many cases, an object may not complete even one full orbit over the entire age of human civilization. This slowness is part of what defines the Oort Cloud. Close to the Sun, planetary motion feels active. Mercury completes an orbit in 88 days, Earth in 1 year, Neptune in 165 years. In the Kuiper Belt, orbital periods stretch into hundreds of years. In the scattered disk, thousands of years. But in the Oort Cloud, we move into timescales that are almost geological. An object at 50,000 astronomical units may require millions of years to circle the Sun once. That means that since the rise of dinosaurs, it may have completed only a handful of revolutions. And yet, these objects are still gravitationally bound to the Sun. That fact alone is remarkable. Even at 50,000 astronomical units, the Sun's gravity remains just strong enough to hold on to these distant fragments. But it does so delicately. The binding energy is weak. A passing star drifting within a few light years can alter their orbit significantly. The slow tidal force of the Milky Way's gravitational field can gradually reshape their trajectories. In this sense, the Oort Cloud exists in a balance zone. It is the outermost region where the Sun's gravity dominates more than any other single influence. But it is not immune to external forces. Another detail often overlooked is that the Oort Cloud is likely not perfectly spherical. While long-period comets suggest a roughly isotropic distribution, models indicate that the inner Oort Cloud may be somewhat flattened or elongated. The outer regions may be more spherical due to stronger cumulative perturbations over time. There may be gradients in density, with more objects concentrated toward the inner boundary. This layered structure has led astronomers to distinguish between the inner Oort Cloud, sometimes called the Hills Cloud, and the outer Oort Cloud. The inner region may extend from roughly 2,000 to perhaps 20,000 astronomical units. It could contain a denser population of objects that are more tightly bound to the Sun. These objects are less easily perturbed and may serve as a reservoir feeding the outer cloud. Beyond that lies the outer Oort Cloud, stretching tens of thousands of astronomical units outward. Objects here are only loosely bound. They are the most susceptible to disruption. When we describe the Oort Cloud as made of ice and darkness, the phrase is literal rather than poetic. The composition of these bodies is similar to that of comet nuclei. They are mixtures of water ice, carbon dioxide ice, methane ice, ammonia ice, and rocky dust. They formed in the colder outer regions of the early solar system, where volatile compounds could freeze and accumulate. Over billions of years, these objects have remained frozen. The temperature at 50,000 astronomical units is only a few degrees above absolute zero. Sunlight at that distance is faint beyond everyday comparison. The Sun would appear as a bright star, but it would provide almost no warmth. There is no glow marking the cloud's presence, no illuminated boundary. The only light comes from distant stars and from the Sun itself, reduced to a point source. This invisibility is why we rely on indirect evidence. We detect the Oort Cloud through the comets it occasionally sends inward. Each long-period comet is thought to originate in this distant sphere. When a gravitational disturbance nudges one of these icy bodies onto a slightly altered path, it may begin a long descent toward the inner solar system. As it approaches within a few astronomical units of the Sun, its ices vaporize, forming a coma and tail. It becomes visible. We measure its orbit. We trace its path backward, and often that backward path points to a source tens of thousands of astronomical units away. The distribution of these orbits is what defines the sphere. Another interesting aspect of the Oort Cloud structure involves its interaction with the galaxy. The Milky Way exerts a tidal force on objects within the solar system. This galactic tide is extremely weak compared to the Sun's gravity near the planets. But at distances of tens of thousands of astronomical units, the galactic tide becomes significant. It can slowly stretch and reshape the orbits of Oort Cloud objects. Over millions of years, it may increase the likelihood that some objects are nudged inward. Passing stars also play a role. As the Sun orbits the centre of the galaxy, it occasionally passes relatively near other stars. Near, in astronomical terms, might mean within a light year or two. Even at those distances, a star's gravity can perturb the outer Oort cloud. This means the Oort cloud is not static. It is dynamic on long timescales. Objects are gradually lost to interstellar space. Others may be sent inward. The cloud slowly evolves. And yet, despite this ongoing change, its overall scale remains immense. To appreciate just how immense, consider this simple comparison. If you compressed the entire planetary system out to Neptune's orbit into a circle the size of a coin, then the outer boundary of the Oort cloud would lie many kilometres away. The planets occupy only a tiny central region compared to the vast sphere that may surround them. This realization shifts perspective. When we speak casually of the solar system, we often imagine the Sun and its planets. Perhaps we include Pluto and the Kuiper Belt. Rarely do we picture a sphere extending nearly halfway to the nearest star. But if the Oort cloud exists as described, then the true physical extent of the solar system is not defined by the last planet. It is defined by the farthest icy body still bound to the Sun, and that boundary may lie more than a light year away. Trying to answer how big the Oort cloud really is forces us into a more uncomfortable question first. What do we actually mean when we say something is big? On Earth, size is intuitive. A mountain is big because you can see it rising above the horizon. An ocean is big because crossing it takes days. Even a planet, though vast, can be compared to something tangible. You can say Jupiter is 11 times wider than Earth, and that ratio has meaning because both are objects we can imagine as spheres. But once we leave planetary scales behind, our sense of proportion begins to fail quietly. We have already spoken about astronomical units. One astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometres. That number alone is too large for the human brain to visualise directly. So astronomers use the astronomical unit as a shorthand, a way to compress the scale of the solar system into manageable units. Neptune orbits at about 30 astronomical units. The Kuiper Belt extends to perhaps 50 astronomical units. Some scattered objects reach 100 astronomical units or more. These are already large numbers, but they remain within a range where we can at least stack them up in our minds. Then the Oort cloud appears, and the numbers shift dramatically. If the inner Oort cloud begins around 2,000 astronomical units, that is 40 times farther from the Sun than the outer edge of the Kuiper Belt. If the outer Oort cloud extends to 50,000 astronomical units, that is 1,000 times farther than Neptune's orbit. If it reaches 100,000 astronomical units, we're talking about 1.6 light years. At this point, the astronomical unit itself starts to feel small, almost insufficient. So astronomers switch units again and begin speaking in light years. A light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. In a single second, it can circle Earth more than 7 times. In 1 year, it travels about 9.46 trillion kilometers. When we say the outer Oort cloud may extend 1.6 light years from the Sun, that means sunlight takes more than a year and a half to travel from the Sun to the cloud's outer boundary. That is a very different mental image from the 8 minutes it takes sunlight to reach Earth. Here is one way to ground it. Imagine shrinking the solar system so that the distance from Earth to the Sun, 1 astronomical unit, is 1 metre. In this model, Neptune would orbit at 30 metres. The Kuiper Belt would extend to around 50 metres. Sedna's farthest distance might reach 900 metres. Now extend that same scale outward. The inner edge of the Oort cloud at 2,000 astronomical units would lie 2 kilometres away from the Sun. The outer edge at 50,000 astronomical units would be 50 kilometres away. At 100,000 astronomical units, it would be 100 kilometres away. On this scale, the entire planetary system fits comfortably inside a small park. The Oort cloud stretches across a region larger than a city. And even that analogy understates something important, because the Oort cloud is not a flat disk like a park, it is a sphere. Volume increases dramatically with radius. If you double the radius of a sphere, you increase its volume 8-fold. If you increase the radius by a factor of 1,000, you increase the volume by a factor of 1 billion. That means that even if the density of objects in the Oort cloud is extremely low, the total number of objects could still be enormous simply because the region is so vast. Some models estimate there could be hundreds of billions or even trillions of icy bodies in the Oort cloud. These numbers are uncertain, but they are consistent with the rate at which long-period comets appear in the inner solar system. Now, here is the subtle part. When people hear that the Oort cloud may extend nearly halfway to the nearest star, they sometimes imagine a smooth gradient of solar influence that fades neatly into interstellar space. In reality, the boundary is not sharp. The Sun's gravity decreases with distance according to an inverse square law. That means if you double your distance from the Sun, its gravitational pull becomes 4 times weaker. At tens of thousands of astronomical units, the Sun's pull is extremely faint, but it is still present. At some distance, however, the gravitational pull of the Milky Way becomes comparable. The Sun orbits the centre of the galaxy at roughly 220 kilometers per second. As it does so, it experiences tidal forces from the galaxy's mass distribution. These galactic tides can gradually alter the orbits of Oort cloud objects. Passing stars can do the same. So when we ask how big the Oort cloud is, we're really asking how far outward the Sun's gravitational dominance extends before it becomes overwhelmed by other influences. Estimates of 50,000 to 100,000 astronomical units are based on this balance. Inside that range, most objects are still more strongly bound to the Sun than to the galaxy. Beyond that range, objects are more easily stripped away. The boundary is therefore statistical rather than physical. This is different from the surface of a planet, where there is a clear transition from solid ground to atmosphere, and then to space. In the case of the Oort cloud, there is no visible edge. There is only a gradual thinning of bound objects until their numbers become negligible. Another way to approach big in this context is through time. Orbital period increases with distance. According to Kepler's third law, the time it takes an object to orbit the Sun grows rapidly as its distance increases. An object at 1 astronomical unit takes 1 year to orbit. At 4 astronomical units, it takes 8 years. At 100 astronomical units, it takes roughly 1,000 years. At 10,000 astronomical units, it takes about 1,000,000 years. At 50,000 astronomical units, an object may require several million years to complete a single orbit. That means that if you could watch the Oort cloud in accelerated time, you would see an extremely slow choreography. Objects would drift almost imperceptibly. Their motions would be subtle and prolonged. In this sense, big is not only about spatial extent, it is about time scale. The Oort cloud occupies a domain where spatial and temporal scales both stretch beyond ordinary experience. There is also a psychological aspect to this question. When we say something is big, we often mean it is big relative to us. The Pacific Ocean is big because crossing it takes days or weeks. Jupiter is big because it dwarfs Earth. But the Oort cloud challenges this relational thinking. It is big not just relative to Earth, but relative to the entire planetary system. It is big compared to the Kuiper Belt. It is big compared to the heliosphere. It is big compared to anything humans have directly explored. In fact, if we define the solar system by the Oort cloud's outer boundary, then the region occupied by the 8 planets is a tiny inner core. If you imagine the Oort cloud as a sphere 100 kilometers in radius, in our earlier scaling analogy, then the orbit of Neptune at 30 meters lies almost invisibly close to the center. This perspective alters the meaning of solar system. It becomes less about planets and more about gravitational reach. Another useful comparison involves interstellar distances. The average distance between stars in our region of the Milky Way is several light years. If the Oort cloud extends 1.6 light years, then the Sun's gravitational domain overlaps significantly with the average interstellar spacing. This means that while the Sun is clearly a distinct star, its gravitational presence extends far into what we casually call interstellar space. That overlap also explains why passing stars can perturb the outer Oort Cloud. Over the billions of years since the Sun formed, it has likely experienced many close stellar encounters at distances of a few light years or less. Each encounter may have subtly reshaped the cloud, nudging some objects inward and ejecting others outward. So when we ask how big the Oort Cloud is, we are not just measuring a static structure. We are measuring a dynamic boundary shaped by interactions with the galaxy. And yet, despite all of these complexities, the central fact remains simple. The Oort Cloud, if it extends to 50,000 or 100,000 astronomical units, represents a region that is 1,000 times farther from the Sun than Neptune's orbit. It may extend nearly halfway to the nearest star. It encloses a volume billions of times larger than the inner solar system. That is what big means in this context. It is not merely large, it is vast in a way that compresses the familiar planetary system into a small inner feature. At some point in any discussion about the outer reaches of the solar system, the numbers themselves begin to push back. They stop behaving like helpful descriptors and start feeling like obstacles. Astronomical units, light years, billions of kilometers, millions of years. Each term is precise, each one is necessary, and yet taken together they can feel more confusing than clarifying. This is not a failure of intelligence, it is a limitation of human intuition. Our brains evolved to judge distances measured in footsteps, fields, valleys, and horizons. We are good at estimating how long it takes to walk to the next building or drive across a city. We are reasonably good at imagining the size of a mountain or the width of an ocean. But the moment distance is no longer connected to effort, time, or physical experience, the mental anchors fall away. So before we can meaningfully say how big the Oort Cloud really is, we need to slow down and make peace with the units we're using, because without that grounding, phrases like 50,000 astronomical units or 1.5 light years become empty labels, accurate but hollow. Let's begin with the astronomical unit, since it is the backbone of solar system measurements. An astronomical unit, abbreviated AU, is defined as the average distance between Earth and the Sun. That distance is about 150 million kilometers. The number itself is already far beyond everyday experience, which is why astronomers almost never use kilometers when talking about planetary distances. The AU compresses that immensity into a single, manageable step. Earth is 1 AU from the Sun. Mars averages about 1.5 AU. Jupiter orbits around 5 AU. Neptune sits near 30 astronomical units. These numbers form a ladder that makes sense within the context of the planets. You can climb it gradually. Each rung is bigger, but not absurdly so. Even the Kuiper Belt fits reasonably well into this framework. Extending to about 50 astronomical units, it represents a region not dramatically larger than Neptune's orbit. When we talk about objects at 100 astronomical units, we're still within a scale where the astronomical unit remains intuitive. 100 is a number the brain can hold without strain. The trouble begins when the AU stops being a convenient compression and starts becoming a very small unit relative to what it is describing. The inner edge of the Oort Cloud may begin around 2,000 astronomical units. That is already a leap of 2 orders of magnitude beyond Neptune. The outer edge may lie at 50,000 astronomical units or more. At that point, the AU is no longer doing the job it was designed to do. It forces us to juggle numbers so large that comparison becomes difficult. This is where astronomers switch to light years. A light year is not a unit of time. That misunderstanding is common and persistent. A light year is a distance, defined as how far light travels in 1 year. Light moves at about 300,000 kilometers per second. Over the course of a year, that adds up to roughly 9.46 trillion kilometers. So when we say something is 1 light year away, we are saying that the light we see today left that object 1 year ago. Earth is about 8 light minutes from the Sun. Neptune is about 4 light hours away. The Kuiper Belt lies perhaps 6 to 8 light hours out. Even Sedna at its farthest is only a few light days away. The Oort Cloud is different. At 50,000 astronomical units, the distance from the Sun is about 0.8 light-years. At 100,000 astronomical units, it is about 1.6 light-years. That means light from the Sun takes more than a year to reach the outermost regions of the cloud. That single fact changes the scale of the conversation. Everything we normally think of as the solar system exists within a bubble measured in hours of light travel. The Oort Cloud exists on a scale measured in years of light travel. That is not a subtle difference. It is a fundamental shift. Now, here is where the headache often sets in. Astronomers casually move between astronomical units and light years depending on context. This is efficient for professionals, but for anyone trying to build an intuitive picture, it can feel like the ground is constantly shifting. One moment we are counting in tens, the next in tens of thousands. Then suddenly we are talking about fractions of a light year. To make matters worse, light years are more commonly associated with distances between stars and galaxies. When people hear light year, they tend to think they are no longer talking about the solar system at all. And yet the Oort Cloud forces us to use stellar scale units to describe something that still belongs gravitationally to the Sun. That alone should signal just how unusual this structure is. Another source of confusion lies in the way these units relate to time. When you hear that an object is 1 light year away, you might instinctively associate that with a year of travel. But nothing humans have ever built moves anywhere close to the speed of light. Voyager 1, the fastest spacecraft ever launched relative to the Sun, travels at about 17 kilometers per second. At that speed, it would take roughly 18,000 years to travel 1 light year. So when we say the Oort Cloud may extend 1.6 light years from the Sun, we're also saying that reaching its outer edge at Voyager's speed would take on the order of 30,000 years. That is longer than the entire span of recorded human history. This is why analogies are often used, but analogies come with their own problems. One common analogy shrinks the solar system down so that the Sun is the size of a marble. In that model, Earth might orbit a few meters away. Neptune would orbit tens of meters away. The Kuiper Belt might extend out to the edge of a football field. The Oort Cloud, in the same model, would stretch for kilometers. That is helpful, but only up to a point. Because even kilometers are distances we can physically traverse. You can walk a kilometer in 10 minutes. You can drive it in seconds. That sense of effort undermines the analogy. Another approach is to think in terms of density. The planetary region feels crowded because planets are relatively close together compared to the size of their orbits. The Kuiper Belt feels sparse but still structured. The Oort Cloud is sparse to an extreme degree. Objects are separated by distances that dwarf the size of the objects themselves. This sparsity is part of what makes the Oort Cloud difficult to imagine as a cloud at all. It is not a fog. It is not a swarm. It is more like a collection of distant islands in a vast ocean of emptiness. When astronomers estimate the size of the Oort Cloud, they are not drawing a hard boundary. They are identifying a region where the probability of finding sun-bound objects drops off sharply. Inside the inner Oort Cloud, objects are relatively more stable. Beyond the outer Oort Cloud, the Sun's gravitational hold is so weak that objects are easily stripped away by galactic tides or passing stars. That transition does not occur at a single distance. It occurs over a range. This is why you will see different numbers quoted in different sources. Some will say 50,000 astronomical units. Others will say 100,000 astronomical units. Some will give values in light years. None of these are wrong. They are describing a fuzzy boundary using different criteria. The headache comes from expecting precision where the universe offers gradients. Another mental trap involves volume versus radius. When we hear that the Oort Cloud extends 1,000 times farther than the Kuiper Belt, we might assume it is 1,000 times bigger. But that intuition ignores volume. A sphere with a radius 1,000 times larger has a volume 1 billion times greater. This means that even if the Oort Cloud contains only a modest increase in total mass compared to the Kuiper Belt, it occupies an incomprehensibly larger region of space. This is why the Oort Cloud can be both enormous and nearly empty at the same time, and this is where units alone fail us. Saying 1 billion times the volume does not help unless you have a reference for what that volume means. Without a way to anchor the concept, the phrase simply floats past the mind. Another source of confusion arises when people mix up observational reach with physical extent. We can see galaxies billions of light years away. That does not mean we can easily see objects 1 light year away if those objects are small and dark. The Oort Cloud sits in an awkward observational regime. It is extremely close compared to galaxies, but extremely faint and diffuse. Its members do not emit light. They reflect almost none. They are invisible against the background of stars. So when people hear that astronomers can see billions of light years away, but cannot see the Oort Cloud, it feels contradictory. It is not. Visibility depends on brightness, size, and contrast, not just distance. A galaxy contains hundreds of billions of stars. Even from millions or billions of light years away, their combined light is detectable. An icy body a few kilometers across at 50,000 astronomical units reflects almost nothing. Distance is not the limiting factor. Signal strength is. Understanding this helps clarify why the Oort Cloud remains hypothetical rather than observed directly. Another subtle headache comes from the way language frames ownership. We speak of the Oort Cloud as part of the solar system. That suggests a sense of inclusion. But at distances approaching a light year, the distinction between solar and interstellar space becomes blurred. Objects at the outer edge of the Oort Cloud are only weakly bound to the Sun. Their orbits can be altered significantly by galactic tides. Some may eventually drift away, others may be captured temporarily. This means that the solar system's boundary is not static. It shifts over time. So when we ask how big the Oort Cloud is, we are asking a question that has no single permanent answer. It depends on how strongly bound you require an object to be. It depends on how long you are willing to wait before calling that binding temporary rather than permanent. It depends on whether you care more about current configuration or long-term stability. These are subtle distinctions, but they matter. All of this is why talking about the size of the Oort Cloud often feels mentally exhausting. The units are large, the boundaries are fuzzy, the timescales are immense, the objects themselves are invisible, and yet this difficulty is not a flaw. It is a clue. It tells us that the Oort Cloud sits at the limit of human-scaled thinking. It occupies a regime where solar system science overlaps with galactic dynamics, where astronomical unit-scale thinking gives way to light-year-scale thinking, where planetary intuition no longer applies. That is precisely why the Oort Cloud is so important. It forces us to confront the fact that the Sun's influence extends far beyond the bright, orderly region of planets. It forces us to stretch our definitions and our units until they begin to creak. One way to get past the frustration of astronomical units and light years is to stop treating them as numbers altogether. Numbers alone, once they grow large enough, stop doing any real work for the imagination. They sit there, technically correct, emotionally empty. To make sense of the Oort Cloud's size, we need to compress the solar system into something almost physical. Not realistic, not accurate in detail, but scaled in a way the mind can move through without breaking. So let's try a simple thought experiment. Imagine the Sun reduced to the size of a marble. Not a glowing one, not a hot one, just a smooth glass marble sitting on the ground. This marble represents the Sun in its entirety, with all of its mass, gravity, and influence shrunk down to something you could hold between 2 fingers. Now, scale everything else accordingly. At this scale, Earth would not be anywhere near that marble. Earth would be a grain of dust about the size of a speck of pollen, orbiting roughly 15 meters away. That is about the length of a large room or a small classroom. Between the marble Sun and that tiny grain of Earth, there would be nothing at all. Just empty space. Already this model begins to challenge intuition. We are used to illustrations where planets appear clustered close together, with colourful orbits drawn neatly around a central star. In reality, even when scaled down dramatically, the distances dominate. Now let's move outward. Mars would orbit around 23 metres away. Jupiter, the giant of the planetary system, would still be just a small bead, about the size of a peppercorn, orbiting roughly 78 metres from the marble Sun. That is nearly the length of a football field. Saturn would orbit around 140 metres away. Uranus would lie nearly 300 metres out. Neptune would orbit around 450 metres from the marble. At this point, the planetary system already fills a large open space. You could stand near the marble Sun and struggle to see Neptune at all, even if you knew exactly where to look. This is where many mental models quietly stop. Neptune feels far. It feels final. But in our scaled-down solar system, Neptune is still less than half a kilometre from the Sun. Now, let's add the Kuiper Belt. The Kuiper Belt would begin just beyond Neptune and extend outward to roughly 750 metres from the marble Sun. Pluto and similar objects would orbit in this region, still less than a kilometre away. So far, everything that most people casually think of as the solar system fits comfortably within a circle less than a kilometre in radius. Now pause, take a breath, because what comes next is where the scale changes completely. The inner edge of the Oort Cloud, at around 2,000 astronomical units, would lie roughly 30 kilometres away from the marble Sun. Not metres, kilometres. That is the distance across a small city. If the marble Sun were placed in the centre of town, the inner Oort Cloud would begin somewhere well beyond the suburbs. You could drive for half an hour and still not reach it. Everything we have discussed so far, every planet, every asteroid, every Kuiper Belt object would fit inside a space smaller than a single city block in comparison. And that is only the beginning of the Oort Cloud. The outer edge of the Oort Cloud at 50,000 astronomical units would lie roughly 750 kilometres away from the marble Sun. 750 kilometres. That is the distance between major cities. That is the distance you might fly on a short commercial flight. That is not something you casually cross in a day. If the marble Sun were placed in one city, the outer Oort Cloud would lie hundreds of kilometres away, perhaps across an entire country. If we extend the estimate to 100,000 astronomical units, the distance doubles. The outermost boundary would lie around 1,500 kilometres away. That is the distance across multiple countries. That is the distance between major regions of a continent. And remember, this is not a flat disk. This is a sphere. The Oort Cloud would surround the marble Sun in all directions, extending hundreds or thousands of kilometres outward, above you, below you, in every direction you could point. In this model, the planetary system occupies an almost laughably tiny central region. The Oort Cloud dominates the map. Now consider density. In the planetary region, objects are relatively close together. In the Kuiper Belt, they are farther apart but still part of a recognisable structure. In the Oort Cloud, the nearest object to you might still be tens or hundreds of kilometres away on this scale. There would be no visible ring, no haze, no boundary you could point to. If you were somehow standing somewhere inside this scaled Oort Cloud, you would likely see nothing at all that belonged to the Sun. The marble would be far beyond the horizon. The icy bodies would be too distant to spot. Only the background stars would be visible. This is why the Oort Cloud remains invisible in reality. Not because it is small, but because it is too large and too sparse. Now let's bring time into this model. Imagine one of these icy bodies orbiting the marble Sun at a distance of, say, 500 kilometres in our scaled version. Its orbital path would be enormous. It would take millions of years in real time to complete a single orbit. In the scaled model, that motion would be so slow that you could watch it for days, months, even years, and see no noticeable change. Motion in the Oort Cloud is not dynamic in the way planetary motion is dynamic. It is glacial, almost static. This slowness matters because it explains why the Oort cloud can remain intact over billions of years while still being vulnerable. A passing star, even one that never comes particularly close in astronomical terms, can alter these distant orbits. In our marble model, imagine another marble-sized sun passing a few kilometers away. Even at that distance, its gravity could tug on the outermost objects, slightly changing their paths. Over time, some would drift inward, others would drift outward and escape. This is not hypothetical. It is expected behavior. The Sun orbits the center of the Milky Way once every 225 to 250 million years. During that journey, it passes near other stars. Some encounters are closer, others are farther. Each one reshapes the distant cloud just a little. Over billions of years, these small effects add up. So when we draw the Oort cloud as a static sphere with a neat boundary, we are simplifying. In reality, it is a living structure on cosmic timescales. Objects drift in and out. The outer edge breathes, expands, contracts. In the marble model, the Oort cloud is not a wall. It is a fading probability field. The farther you go, the less likely you are to find an object still bound to the Sun. Now consider one more comparison. The nearest star to the Sun, Alpha Centauri, would lie about 2,000 kilometers away from the marble Sun in this model. That means the outer Oort cloud at 1,500 kilometers extends more than halfway to the nearest star. Let that settle. The Sun's gravitational influence reaches out across a distance that overlaps significantly with the region between stars. This means that, on a galactic scale, stars are not isolated points with neatly separated territories. Their outermost gravitational domains brush against one another. Sometimes they interact, sometimes they exchange material. It is entirely possible that some objects in the outer Oort cloud did not originate with the Sun at all. They may have been captured from other stars during close encounters early in the solar system's history. Likewise, the Sun may have lost some of its original material to other stars' clouds. The Oort cloud is not just the edge of the solar system, it is also the interface between the solar system and the galaxy. Returning to the marble model one last time, think about perspective. If you were given a map showing only the region within 1 kilometer of the marble Sun, you would see everything familiar. Planets, Kuiper Belt, order, structure. If you zoomed the map out to include 50 kilometers, you would see nothing new, just empty space. If you zoomed out to 500 kilometers, you might still see nothing. Only when you zoomed out to hundreds or thousands of kilometers would the Oort cloud begin to matter. This explains why, for centuries, the solar system was thought to end at the planets. Not because people were careless, but because their observational tools and conceptual maps simply did not extend far enough. Even today, our spacecraft have barely left the central kilometer of this scaled model. Voyager 1, at about 160 astronomical units, would lie just over 2 meters from the marble Sun. 2 meters. Everything beyond that, everything that dominates the true size of the solar system, remains completely unexplored. This is a humbling realization. The Oort cloud is not an obscure footnote. It is the majority of the solar system's physical extent. The planets occupy the tiniest inner fraction of the Sun's domain. When people ask how big the Oort cloud really is, the most honest answer may be this. It is so large that even extreme scaling still leaves it sprawling across distances that feel geographic rather than astronomical. And yet, despite that size, it remains quiet, invisible, patient. It does not announce itself. It does not glow. It reveals its existence only through rare visitors, comets that fall inward and briefly remind us that the Sun's reach extends far beyond the bright, orderly region we call home. Once you begin to grasp the scale of the Oort cloud, a new question naturally follows. If this distant sphere is so vast, how many objects could it possibly contain? It is a simple question in wording, but a difficult one in practice. Unlike counting planets or even Kuiper Belt objects, we cannot scan the Oort cloud with telescopes and tally what we see. The cloud is too distant, too faint, and its members are too small and dark to observe directly. So instead of counting objects, astronomers estimate them. That distinction matters. When you hear that the Oort Cloud may contain trillions of icy bodies, that number is not the result of direct observation. It is the result of modelling, statistics, and inference drawn from the behaviour of comets that briefly visit the inner solar system. To understand how these estimates are made, we need to return to the long-period comets that first inspired Jan Oort's proposal. Each time a long-period comet appears, astronomers calculate its orbit carefully. They determine how elongated it is, how long it takes to complete a full revolution around the Sun, and how strongly it is bound gravitationally. By tracing the comet's path backward, they can estimate how far from the Sun it likely originated. When enough of these comets are studied, patterns emerge. Astronomers can estimate how frequently new long-period comets enter the inner solar system. They can measure how many appear per year, per decade, per century. From that rate, they work backward. If, for example, a certain number of comets are observed entering the inner solar system each year, and if models of gravitational perturbations suggest that only a tiny fraction of Oort Cloud objects are nudged inward over a given timescale, then the total population must be large enough to sustain that influx over billions of years. This reasoning leads to estimates that the Oort Cloud could contain on the order of hundreds of billions to trillions of icy bodies larger than a few kilometres across. But these numbers come with uncertainty. First, we do not detect every long-period comet. Many are faint. Some approach the Sun on trajectories that make them difficult to observe from Earth. Others disintegrate before becoming bright enough to notice. Our observational record is incomplete. Second, the rate at which comets are nudged inward depends on complex gravitational influences. Passing stars, galactic tides, and planetary perturbations all play a role. Small changes in these assumptions can lead to large changes in estimated population size. Even with these uncertainties, however, most models agree that the Oort Cloud likely contains far more objects than the Kuiper Belt. The Kuiper Belt may hold millions of objects larger than 1 kilometre. The Oort Cloud, by contrast, may hold trillions. That difference is not just incremental, it reflects the sheer volume of space the cloud occupies. Earlier we discussed how the volume of a sphere increases with the cube of its radius. If the Oort Cloud extends 1,000 times farther than the Kuiper Belt, its volume could be roughly 1 billion times greater. Now, this does not mean it contains 1 billion times more mass. The density of objects decreases dramatically with distance. The cloud is sparse, extremely sparse. If you were floating somewhere within the Oort Cloud, the nearest object might be tens of millions of kilometres away. That is farther than the distance between Earth and the Moon, perhaps comparable to the distance between planets in the inner solar system. This sparsity is why the cloud remains invisible. Another factor to consider is size distribution. Not all Oort Cloud objects are the same size. Some are likely small fragments, perhaps only a few hundred metres across. Others may be several kilometres in diameter. A small fraction could be tens or even hundreds of kilometres wide. The larger the object, the fewer there are likely to be. This follows a general rule observed throughout the solar system. Small bodies are far more numerous than large ones. So when astronomers say trillions of objects, they are typically referring to bodies above a certain minimum size, often around 1 kilometre in diameter. Below that size, the number of objects could be much higher, but they would contribute little to the overall mass. Speaking of mass, estimates of the total mass of the Oort Cloud vary. Early calculations suggested it might contain several Earth masses of material. More recent models tend to favour lower values, perhaps around 1 to a few Earth masses in total. That might sound like a lot, but remember how vast the volume is. Spread across a sphere tens of thousands of astronomical units in radius, even several Earth masses amount to a very low average density. For comparison, the mass of Jupiter alone is more than 300 times the mass of Earth. All of the Oort Cloud combined likely contains less mass than a single giant planet. This tells us something important. The Oort Cloud is large in extent, but not in mass concentration. It is a dispersed archive of leftover building blocks, not a hidden giant planet. Another interesting question is how many of these objects have ever visited the inner solar system. Each long-period comet that approaches the Sun represents one of these distant bodies temporarily drawn inward. Some may pass once and then be ejected from the solar system entirely. Others may be captured into shorter period orbits, gradually losing mass over repeated passes. Over billions of years, countless Oort Cloud objects have likely made this journey inward. This process gradually depletes the cloud. So how has it survived for 4.5 billion years? The answer likely lies in its size. If the initial population was extremely large, then even a steady trickle of inward comets would not exhaust it quickly. Additionally, the inner Oort Cloud may act as a reservoir, feeding the outer regions and replenishing objects lost to interstellar space. There is also the possibility of capture. Occasionally, interstellar objects pass near the Sun. We have direct evidence of this in the form of objects like Oumuamua and Comet Borisov, which entered the solar system from interstellar space. If such objects pass close enough and at the right speed, it is theoretically possible for them to become gravitationally bound to the Sun, joining the distant cloud. This would mean the Oort Cloud is not purely a collection of native solar system material. It could include interstellar immigrants as well. Another layer of uncertainty comes from the cloud structure. Astronomers often distinguish between the inner Oort Cloud and the outer Oort Cloud. The inner region may be more densely populated and more tightly bound to the Sun. The outer region may be sparser and more vulnerable to disruption. If the inner cloud contains most of the mass, then the outer cloud may act primarily as a source of long-period comets. Some models even suggest that the inner Oort Cloud could contain 10 times as many objects as the outer cloud, though these numbers are highly uncertain. All of these estimates depend on assumptions about the early solar system. How many planetesimals were scattered outward by Jupiter and Saturn? How densely packed was the Sun's birth cluster? How frequently did other stars pass nearby in the early days? How strong are galactic tidal forces over billions of years? Each of these variables influences the final population. Because we cannot observe the cloud directly, we rely on computer simulations to test different scenarios. These simulations track millions of virtual objects over billions of simulated years, modelling gravitational interactions and perturbations. When the output of these simulations matches the observed distribution of long-period comets, astronomers gain confidence that the assumed population size is plausible. It is a kind of reverse engineering. We observe the comets that arrive, we infer the size of the distant reservoir needed to supply them, and yet, even with all of this modelling, there remains a wide margin of uncertainty. The Oort Cloud could contain hundreds of billions of objects. It could contain trillions. The true number might lie somewhere in between. What is clear is that the cloud represents a vast population of icy remnants, far exceeding the number of large bodies in the planetary region, and this has implications beyond simple counting. Each of those objects is a frozen relic of the early solar system. Preserved at extreme distances and low temperatures, they may contain pristine material from the time when the Sun and planets were forming. Long-period comets that reach the inner solar system offer rare opportunities to study this material. They are samples delivered from the outermost archive. So when we ask how many objects are out there, we are not merely asking for a statistic. We are asking how extensive this ancient archive might be. A sphere stretching nearly halfway to the nearest star, containing perhaps trillions of icy fragments, each one orbiting in silence for millions of years. That is the scale of the population we are considering. Long before the outer reaches of the Oort Cloud begin to fade into the gravitational background of the galaxy, there is another region that demands attention. It is closer, denser, and far more tightly bound to the Sun, yet it remains just as unseen. This is what astronomers refer to as the inner Oort Cloud, sometimes called the Hills Cloud, a hidden shell of icy bodies occupying the deep outer reaches of the Sun's gravitational domain. It is called hidden not because it is mysterious in a dramatic sense, but because it sits at a distance where direct observation becomes almost completely impractical. Even compared to the Kuiper Belt and scattered disk, the inner Oort cloud lies far beyond the reach of routine telescopic surveys, and yet paradoxically, it may contain a substantial fraction of the Oort cloud's total population. To understand why astronomers believe such a region exists, it helps to return to the problem that first motivated the idea of the Oort cloud itself. Long-period comets arrive from all directions, but their behaviour is not uniform. Some appear to originate from extremely distant orbits, barely bound to the Sun. Others seem to come from orbits that are distant but not quite so fragile. When researchers began running detailed simulations of comet dynamics, they noticed something interesting. A single, uniform cloud extending from a few thousand astronomical units all the way to the Sun's gravitational limit did not always reproduce the observed comet behaviour very well. The numbers worked better when the cloud was layered. In these models, an inner reservoir of objects sits closer to the Sun, more securely bound, and more resistant to disruption. This inner population acts as a long-term storage zone, slowly feeding objects into the outer cloud and occasionally into the inner solar system. The inner Oort cloud is thought to begin somewhere around 2,000 astronomical units from the Sun. Some estimates place its outer boundary at around 20,000 astronomical units. Others extend it farther. The exact numbers vary, but the key idea remains the same. This is a region far beyond the Kuiper Belt and scattered disk, yet significantly closer than the most distant reaches of the outer Oort cloud. At 2,000 astronomical units, sunlight from the Sun takes about 11 days to arrive. At 10,000 astronomical units, that travel time stretches to nearly 2 months. At 20,000 astronomical units, it takes more than 3 months. These are distances where the Sun is no longer a dominating presence in any visual or thermal sense, but where its gravity still holds firmly. This firmness is what distinguishes the inner Oort cloud from the outer one. Objects in the inner cloud are more tightly bound to the Sun. Their orbits, while elongated and tilted, are less susceptible to being stripped away by passing stars or by the slow pull of the Milky Way's gravitational field. They are still vulnerable, but not precariously so. This stability makes the inner Oort cloud especially important when considering the long-term survival of the entire structure. Over billions of years, the outer Oort cloud is expected to lose a significant number of objects. Some are ejected by stellar encounters, others drift away under galactic tides. Without a replenishing source, the outer cloud would gradually thin out. The inner Oort cloud may be that source. In many models, objects from the inner cloud are slowly transferred outward through gravitational interactions. Once they reach the outer cloud, they become more vulnerable and can eventually be perturbed inward as long-period comets. In this view, the inner Oort cloud is not merely a passive region. It is an active reservoir, maintaining the supply of distant icy bodies over cosmic timescales. This idea also helps address another puzzle. If the Oort cloud formed early in the solar system's history, when the Sun was still embedded in a dense stellar cluster, then close stellar encounters would have been more common. Such encounters could have stripped away loosely bound objects, especially from the outer regions. A more tightly bound inner cloud would have been more resistant to this early erosion, even as the Sun migrated out of its birth cluster and into a quieter region of the galaxy. The inner cloud could have survived largely intact. That survival would explain why the Oort cloud still exists today, billions of years later. The shape of the inner Oort cloud is also likely different from that of the outer cloud. While the outer cloud appears roughly spherical, the inner cloud may be more flattened or elongated. Some simulations suggest it could retain a memory of the original plane of the solar system, at least to a degree. Over time, perturbations would still randomize orbits, but not as completely as in the outer regions. This means the inner Oort cloud may not be a perfect shell. It may be more like a thick, distorted halo, transitioning gradually into the fully spherical outer cloud. Because of its location, the inner Oort cloud is also the most plausible source of objects like Sedna. Sedna's orbit is unusual. Its closest approach to the Sun is far beyond Neptune, and its farthest distance reaches nearly 1,000 astronomical units. It does not appear to be strongly influenced by the known planets. Its orbit suggests it was shaped by forces acting at much greater distances. Sedna may be a member of the inner Oort Cloud, or at least a transitional object between the scattered disk and the inner cloud. Other similar objects have been discovered. Though they are rare and difficult to detect, these discoveries lend weight to the idea that the inner Oort Cloud exists and that it begins closer to the Sun than the outer cloud. Another reason astronomers take the inner Oort Cloud seriously is related to efficiency. If the Oort Cloud consisted only of an extremely distant outer shell, it would be difficult to maintain the observed rate of long-period comets over billions of years. Too many objects would be lost too quickly. The numbers would not add up unless the initial population were implausibly large. By introducing a denser inner reservoir, models become more realistic. The inner cloud can act as a buffer, slowly resupplying the outer cloud and maintaining the comet flux we observe today. This layered structure also affects how comets enter the inner solar system. An object in the inner Oort Cloud is less likely to be directly perturbed into a sun-grazing orbit. Instead, it may first be nudged outward into the outer cloud, where it becomes more vulnerable to further perturbations. Only then does it have a significant chance of being sent inward as a long-period comet. This two-step process helps explain why long-period comets are relatively rare despite the enormous size of the Oort Cloud. The inner Oort Cloud may also play a role in shaping the distribution of cometary energies. Some long-period comets appear to be more tightly bound to the Sun than others. This suggests they originated from a region where gravitational binding was stronger, consistent with an inner cloud source. Others arrive on orbits that are barely bound, suggesting an origin in the outer cloud. Taken together, these observations point toward a multi-layered structure rather than a single homogeneous shell. Now consider density again, but with more nuance. The inner Oort Cloud is still extremely sparse by everyday standards. Objects are separated by vast distances, but compared to the outer cloud it may be relatively crowded. Crowded here does not mean close, it means less distant. If the outer cloud contains trillions of objects spread across an enormous volume, the inner cloud may contain a comparable number concentrated into a much smaller volume. This would increase its average density significantly, even if that density remains extraordinarily low. This distinction matters because density influences how often objects interact gravitationally, how stable their orbits are, and how likely they are to be perturbed inward or outward. The inner Oort Cloud's greater density and stronger binding make it more resilient. It is harder to disrupt. It evolves more slowly. This slow evolution is part of what makes it so difficult to study. Changes in the inner cloud occur over millions or billions of years. Human observation spans only a tiny fraction of that time. We see snapshots, not motion. We infer structure from statistical patterns rather than direct evidence. Even with modern telescopes, we're unlikely to ever image the inner Oort Cloud directly. Its objects are too faint. Their reflected sunlight is negligible. They emit no detectable radiation of their own. Future surveys may detect more Sedna-like objects, giving us better constraints on the inner cloud's size and shape. But a detailed map remains out of reach. In this sense, the inner Oort Cloud is one of the largest unseen structures associated with the Sun. It is a hidden shell not because it is imaginary, but because it operates on scales that push beyond observational capability. Another intriguing aspect of the inner Oort Cloud is its potential role as a record of the Sun's early environment. The orbits of its objects may preserve information about how close other stars passed during the solar system's youth. Different encounter histories produce different orbital distributions. By studying the orbits of distant objects, astronomers may eventually be able to reconstruct aspects of the Sun's birth cluster. In that way, the inner Oort Cloud is not just a reservoir of icy debris, it is an archive of dynamical history. Each object carries information about past gravitational interactions. Taken together, they form a fossil record written not in rocks or ice cores, but in orbital parameters. As we move outward in our exploration, the inner Oort Cloud serves as a bridge. It connects the relatively familiar territory of the Kuiper Belt and scattered disk with the extreme, barely bound realm of the outer Oort Cloud. It explains how such a vast structure can persist. It clarifies why the comet population behaves the way it does, and yet, for all its importance, it remains invisible. We know it exists not because we see it, but because without it, the solar system's behaviour would be harder to explain. This hidden shell reminds us that size alone does not determine significance. Sometimes the most important regions are those that quietly maintain balance over immense spans of time. Once you move beyond the inner reservoir, the nature of the solar system changes again. The transition is not abrupt, and there is no clear marker you can point to and say, "Here is where everything shifts." Instead, the structure simply grows thinner, looser, and more vulnerable. This is the outer Oort Cloud, the region that most people have in mind when they hear the phrase at all. It is also the place where the idea of the solar system having an edge becomes difficult to defend. The outer Oort Cloud is often described as the solar system's fuzzy boundary, and that description is more literal than it might sound. Fuzzy does not mean unclear because of ignorance. It means unclear because the physics itself does not produce a sharp line. The farther you go from the Sun, the weaker its gravitational grip becomes, and the more other influences begin to matter. This outer region is thought to begin somewhere beyond the inner cloud, perhaps around 20,000 astronomical units from the Sun. Some models place the transition closer, others place it farther out. The uncertainty exists because the boundary is defined by behaviour rather than location. Objects in this region are still bound to the Sun, but only loosely. Their orbits are extremely elongated. Their binding energy is low. Small disturbances can have large effects. At distances of 20,000 astronomical units, sunlight from the Sun takes nearly 3 months to arrive. At 50,000 astronomical units, it takes over 8 months. At 100,000 astronomical units, light travels for more than a year and a half before reaching these distant bodies. By any intuitive standard, this is no longer the solar system we're used to thinking about, and yet gravity still reaches that far. The defining feature of the outer Oort Cloud is not its size alone, but the delicacy of its balance. Objects here exist in a gravitational tug-of-war. On one side is the Sun, whose pull weakens steadily with distance. On the other side are the combined influences of the Milky Way and passing stars. The Milky Way's gravitational field exerts what astronomers call a galactic tide. This is not a sudden force, but a slow, persistent stretching effect caused by the uneven distribution of mass in the galaxy. Near the Sun, this tidal force is negligible compared to solar gravity. But at tens of thousands of astronomical units, the balance begins to shift. For an object in the outer Oort Cloud, the Sun is no longer the only significant gravitational influence. The galaxy itself starts to matter. This is why the outer Oort Cloud is so effective at producing long-period comets. Galactic tides can gently alter the orbits of distant objects over millions of years. These changes are subtle, but they accumulate. Eventually an object's orbit may be reshaped just enough that its closest approach to the Sun moves inward. Once that happens, the object begins a long fall toward the inner solar system. Passing stars add another layer of complexity. The Sun does not remain stationary. It orbits the centre of the Milky Way, and along that path it occasionally passes relatively close to other stars. Close, in this context, may mean within a light year or two. Even at those distances, a star's gravity can perturb the outer Oort Cloud. Each stellar encounter slightly rearranges the cloud. Some objects are nudged inward, others are pushed outward. A few may be stripped away entirely and lost to interstellar space. Over billions of years, these encounters reshape the cloud again and again. This constant reshaping is why the outer Oort Cloud cannot be thought of as a static shell. It is dynamic, but dynamic on timescales far longer than human history. Changes occur slowly, invisibly, accumulating over epochs. Because of this, the outer boundary of the Oort Cloud is not fixed. It expands and contracts depending on the Sun's environment. Early in the solar system's history, when the Sun was likely part of a dense stellar cluster, close encounters would have been more frequent. During that time, the outer cloud may have been more heavily eroded. Many loosely bound objects could have been stripped away before the Sun ever left its birth cluster. As the Sun migrated into a quieter region of the galaxy, the rate of disruptive encounters decreased. The outer Oort cloud became more stable, though still vulnerable. This history means that the present-day size of the outer Oort cloud reflects not just the Sun's formation, but its entire journey through the Milky Way. Another important characteristic of the outer cloud is its extreme sparsity. Even if it contains trillions of objects, those objects are spread across an enormous volume. The average distance between neighbouring bodies may be measured in millions or tens of millions of kilometres. Collisions are extraordinarily rare. Interactions between objects are minimal. Each follows its own lonely path. This sparsity has consequences. Because objects rarely interact with one another, the structure of the outer Oort cloud is dominated by external forces rather than internal dynamics. Galactic tides and stellar encounters matter far more than mutual gravitational interactions between cloud members. In that sense, the outer Oort cloud is less like a swarm and more like a population of independent travellers who happen to share a common gravitational anchor. This independence also contributes to the randomness of comet arrival directions. When an object from the outer cloud is perturbed inward, the direction it approaches the Sun depends on the specifics of the perturbation. There is no preferred plane, there is no dominant orientation. The result is a nearly isotropic distribution of long-period comets. This isotropy is one of the strongest pieces of evidence supporting the outer Oort cloud's spherical nature. Now consider what happens to objects at the very edge. At distances approaching 100,000 astronomical units, the Sun's gravitational pull is extremely weak. Objects here are barely bound. Their orbits are so fragile that even modest disturbances can unbind them completely. At this boundary, the distinction between solar system object and interstellar object becomes ambiguous. An object drifting in this region may be bound to the Sun for millions of years, then lost during a stellar encounter, then perhaps captured by another star, or simply wander through the galaxy indefinitely. This is why the outer Oort cloud is often described as a transitional zone rather than a boundary. It is the region where the solar system fades into the galaxy rather than ending abruptly. If you were to draw a map of the Sun's gravitational influence, the outer Oort cloud would appear not as a circle with a sharp edge, but as a gradually fading density gradient. The probability of finding sunbound objects decreases with distance, rather than dropping to zero at a specific radius. This probabilistic nature makes the question, where does the Oort cloud end, difficult to answer definitively. Some astronomers define the outer edge as the distance at which the Sun's gravity becomes weaker than the average galactic tide. Others define it as the distance beyond which objects are unlikely to remain bound for more than a few million years. Still others use observational constraints derived from comet energies. Each definition yields a slightly different number. This is why you will see estimates ranging from 50,000 to 100,000 astronomical units, and occasionally even beyond. None of these numbers are wrong. They are describing different aspects of the same fuzzy boundary. Another subtle feature of the outer Oort cloud is its interaction with interstellar space. Because this region overlaps with the broader galactic environment, it may serve as a gateway for material exchange between star systems. Objects stripped from one star's cloud may wander through the galaxy and eventually pass near another star. Some may be captured. This means that the outer Oort cloud may contain objects that did not originate with the Sun at all. The discovery of interstellar objects like Oumuamua and Comet Borisov confirms that such wanderers exist. While those particular objects pass through the inner solar system, many more likely pass through the outskirts unnoticed. If capture is possible, even rarely, Then over billions of years, the outer Oort cloud could accumulate a mixed population. Some objects would be native solar system debris, others would be immigrants. This possibility adds another layer of fuzziness to the boundary. Ownership becomes a matter of timescale rather than origin. An object might be bound to the sun today, unbound tomorrow, and bound again to another star millions of years later. In this context, the outer Oort cloud is not just a reservoir of icy debris, it is a dynamic interface between stars. Now think again about scale. If the outer Oort cloud extends 1.6 light-years from the Sun, and the nearest star lies 4.37 light-years away, then the gap between stars is not empty of influence. The gravitational domains of stars overlap in subtle ways. They brush against each other. This challenges the intuitive picture of stars as isolated islands separated by vast, empty oceans. In reality, their outermost gravitational reaches interpenetrate, creating a complex web of influence across the galaxy. The outer Oort cloud is where this interpenetration begins. This realization has implications for how we define the solar system itself. If we define it by planets, the solar system is compact. If we define it by heliospheric influence, it is larger. If we define it by gravitational binding, it becomes enormous, extending nearly halfway to the nearest star. Each definition is valid within its context, but none captures the whole picture. The outer Oort cloud reminds us that natural systems do not always conform to human categories. They blend, they overlap, they fade rather than end. This fuzziness is not a flaw. It is a feature of systems governed by gravity across immense distances and timescales. Another important consequence of this fuzziness is uncertainty and long-term stability. Objects in the outer Oort cloud are not guaranteed to remain bound forever. Over billions of years, a significant fraction will be lost. The cloud slowly erodes. Estimates suggest that the present-day Oort cloud may contain only a fraction of the objects it once did. The rest have been ejected into interstellar space. This erosion continues today, albeit slowly. At the same time, new objects may be captured. The cloud evolves. In that sense, the outer Oort cloud is not a relic frozen in time. It is an active participant in galactic dynamics. From the perspective of the inner solar system, this activity is almost imperceptible. Long-period comets arrive only occasionally. Most people will never see one in their lifetime. But on cosmic timescales, these arrivals are part of a steady flow. Each long-period comet that appears is evidence of the outer Oort cloud's ongoing interaction with the galaxy. It is a reminder that the solar system is not a closed box. As we move forward, the existence of this fuzzy boundary forces us to confront another question. If the sun's grip weakens gradually, and the galaxy's influence grows stronger with distance, where exactly does the sun lose control? Is there a point beyond which objects are no longer meaningfully part of the solar system at all? And how do astronomers define that transition in practical terms? Far from the warmth and brightness that define the inner solar system, there comes a region where gravity itself begins to hesitate, not because it vanishes, and not because it suddenly fails, but because it is no longer alone. This is the realm where the sun's influence thins, to the point that other forces begin to compete on nearly equal footing. Understanding this region is essential, because it is here that the idea of ownership, of belonging to a star, becomes uncertain. Gravity is often described as infinite in reach, and in a strict mathematical sense that is true. The sun's gravity extends outward without an abrupt cutoff. Its pull weakens with distance, following a simple inverse square law, but it never fully disappears. If that were the only consideration, the solar system would have no edge at all. Every particle in the universe would be influenced, however faintly, by every other particle. In reality, though, gravity operates in a crowded universe. The sun is not alone in space. It is embedded within the Milky Way, surrounded by stars, gas, dust, and dark matter. Each of these contributes to a complex gravitational environment, At close distances, the Sun dominates completely. At great distances, it does not. So when we ask where the Sun loses its grip, we are not asking where gravity ends. We are asking where the Sun stops being the most important gravitational influence acting on an object. Near Earth, the answer is obvious. The Sun's gravity governs planetary motion with overwhelming authority. The gravitational pull of Jupiter, the Moon, or even the galaxy itself is negligible by comparison. As you move outward past the planets, that dominance weakens, but it remains unquestioned through the Kuiper Belt and into the scattered disk. Even within the inner Oort Cloud, the Sun still clearly rules. Objects there are weakly bound, but bound nonetheless. Their orbits are long and tilted, but they are not easily stripped away. A passing star would need to come relatively close to have a dramatic effect. The outer Oort Cloud is different. At distances of tens of thousands of astronomical units, the Sun's gravitational pull has diminished to a whisper. It still shapes motion, but it is no longer overwhelming. Other influences become relevant, not as sudden disruptions, but as persistent, cumulative forces. One of the most important of these is the gravitational field of the Milky Way itself. The galaxy is not a point mass, it is a vast distribution of matter, including stars, gas, and a large halo of dark matter. The Sun orbits the galactic centre at a distance of about 26,000 light-years, moving at roughly 220 kilometers per second. As it does so, it experiences tidal forces caused by the uneven distribution of mass within the galaxy. These galactic tides are extremely weak compared to the Sun's gravity near the planets. But at the outer edge of the Oort Cloud, they become significant. A tidal force works by stretching and compressing objects due to differences in gravitational pull across space. In the case of the Oort Cloud, the galaxy's tidal field can slowly distort the orbits of distant objects, changing their shapes and orientations over millions of years. For an object deep in the outer cloud, this galactic influence can be comparable to the Sun's pull. This balance point is one way to define where the Sun loses its grip. Another important factor is stellar encounters. As the Sun moves through the Milky Way, it occasionally passes near other stars. These encounters are not frequent on human timescales, but over billions of years they are inevitable. A star passing within a light year or two can exert a measurable gravitational influence on the outer Oort Cloud. Such encounters do not need to be close to have an effect. Even at distances far greater than the separation between the Sun and the planets, a passing star can perturb the delicate orbits of distant Oort Cloud objects. Some of these perturbations push objects inward, sending them toward the inner solar system as long-period comets. Others push objects outward, weakening their binding to the Sun until they drift away entirely. Over time, these encounters erode the outer cloud. So where exactly does the Sun lose control? There is no single distance where an invisible line is crossed and an object suddenly becomes free. Instead, there is a gradual transition from strong binding to weak binding to statistical instability. Astronomers often describe this transition using the concept of a gravitational sphere of influence, sometimes called the Hill sphere. In a simplified two-body system, the Hill sphere defines the region around a body where its gravity dominates over that of a larger central mass. In the context of the Sun and the Milky Way, the Hill sphere represents the region where the Sun's gravity dominates over the average galactic gravitational field. Estimates of the Sun's Hill sphere radius vary, but they generally fall in the range of 1 to 2 light-years. That is remarkably close to the estimated outer edge of the Oort Cloud. This is not a coincidence. The Oort Cloud appears to occupy much of the Sun's gravitational sphere of influence within the galaxy. Inside this region, objects are more likely to remain bound to the Sun over long periods. Outside it, they are more likely to be stripped away by galactic tides or captured by other stars. Even within the Hill sphere, stability is not guaranteed. Objects near the boundary may remain bound for millions of years and then be lost during a single stellar encounter. Others may drift in and out of marginal binding states repeatedly. This uncertainty makes the concept of losing its grip inherently probabilistic. At smaller distances, the sun's grip is firm. At greater distances, it is tenuous. Somewhere in between lies a zone where belonging is temporary. This has important consequences for how we define the solar system. If we define the solar system as the region where the sun's gravity is the dominant force, then the solar system extends far beyond the planets, far beyond the Kuiper Belt, and deep into the Oort Cloud. If we define it as the region where objects are guaranteed to remain bound over the age of the solar system, then the boundary lies closer in, perhaps within the inner Oort Cloud. If we define it operationally based on observed populations of objects, then the boundary becomes fuzzy again, stretching outward until the density of bound objects drops below detectability. Each definition yields a different answer, and none of them are wrong. Another way to approach this question is through energy. An object bound to the sun has negative orbital energy relative to the sun. An unbound object has positive energy. Objects near the outer Oort Cloud often have energies very close to zero. Small changes in velocity caused by galactic tides or stellar encounters can flip the sign. In that sense, the outer Oort Cloud is populated by objects living on the edge of escape. This edge is not static. It shifts as the sun moves through different regions of the galaxy. When the sun passes through denser stellar environments, encounters are more frequent and disruptive. When it passes through quieter regions, the cloud is more stable. Over the course of its orbit around the galaxy, the sun has likely experienced many such environments. Early in its history, when it was part of a dense stellar cluster, close encounters may have stripped away large portions of the outer cloud. Later, as the sun settled into a more isolated orbit, the remaining cloud stabilized. This history suggests that the present-day Oort cloud is not the original one. It is what remains after billions of years of erosion. That erosion continues today. Every stellar encounter slightly reshapes the cloud. Every galactic tide subtly alters orbits. The sun is constantly losing some of its distant grip, even as it maintains control over its inner regions. This loss is slow. On human timescales, it is invisible. On cosmic timescales, it is inevitable. Another subtle aspect of losing grip involves capture. Just as the sun can lose objects from its outer cloud, it can also gain them. Interstellar objects occasionally pass near the sun. Most pass through without interaction, but under the right conditions, some could be captured into weakly bound orbits. If this happens, the outer Oort cloud could include objects that did not originate with the solar system at all. These objects would become part of the sun's domain temporarily, perhaps for millions of years, before being lost again. This exchange blurs the distinction between solar system material and interstellar material. Ownership becomes a matter of timing rather than origin. An object may belong to the sun now, belong to another star later, and wander freely in between. This perspective reframes the question of where the sun loses its grip. Rather than asking for a static boundary, it may be more accurate to ask about residence time. How long does an object remain bound? How stable is that binding? How likely is it to persist over billions of years? Within the planetary region, residence times are effectively infinite on cosmic scales. Within the Kuiper Belt, they are extremely long. Within the inner Oort cloud, they are long but not absolute. Within the outer Oort cloud, they are long but fragile. Beyond that, they become temporary. This gradient of stability is more informative than any single distance. It tells us that the solar system is not a closed system with rigid walls. It is an open system interacting continuously with its galactic environment. The sun's grip weakens gradually, not abruptly. It fades rather than breaks. That fading grip explains why the Oort cloud looks the way it does. It explains why long-period comets arrive sporadically. It explains why the cloud is sparse, extended, and vulnerable. It also explains why the Oort cloud may be one of the most dynamic parts of the solar system, despite its apparent stillness. Motion in this region is slow, but change is constant. As the sun continues its journey around the galaxy, it will keep losing and gaining distant companions. The outer cloud will continue to erode and reform. The boundary will continue to shift. From the perspective of the inner solar system, none of this matters very much. The planets will continue to orbit calmly. The sun will continue to shine. Life on Earth will remain unaware. But from a broader perspective, the outer Oort cloud represents the place where the solar system transitions from a tightly bound family to a loosely connected participant in the galaxy. It is where the sun's influence blends into the background of the Milky Way, an understanding that transition prepares us for the next question, which naturally follows. If the sun's grip weakens because of the galaxy and passing stars, then how exactly do those external influences shape the cloud? What role do neighbouring stars play, and how often do they disturb this distant region? Nothing in the galaxy stands still for very long, even if it appears that way from our limited perspective. The sun is moving, other stars are moving. Entire stellar systems drift along their own paths around the centre of the Milky Way. Over millions and billions of years, those paths occasionally bring stars closer to one another than we might expect. Not close in the sense of planetary distances, but close enough for gravity to notice. When two stars pass within a few light years of each other, their planets usually remain undisturbed. The distances between stars are vast compared to the sizes of planetary systems. But the outer Oort cloud occupies a region that stretches far enough outward to overlap with these interstellar approaches. That is where passing stars become important. To understand the role of stellar encounters, it helps to picture the sun travelling through a sparse but dynamic stellar environment. In our neighbourhood of the galaxy, the average distance between stars is roughly 4 to 5 light years. The sun's nearest neighbour, Alpha Centauri, lies about 4.37 light years away. That sounds comfortably distant, and on human timescales it is. However, stars are not fixed relative to one another. Over millions of years, their positions shift dramatically. Astronomers can measure the motion of nearby stars with remarkable precision. By tracing these motions forward and backward in time, they can estimate when close encounters occurred or will occur. These calculations reveal that close stellar passes are not hypothetical. They are routine on galactic timescales. A star may pass within 1 light year of the Sun every few 100,000 to a few million years. Closer passes are rarer but still possible. Over the 4.5 billion year history of the solar system, there have likely been many such encounters. Each encounter, even at distances of a light year or more, exerts a gravitational tug on the outer Oort cloud. The effect of this tug depends on several factors: the mass of the passing star, its relative velocity, and its closest approach distance. A massive star passing slowly at a relatively close distance will have a stronger effect than a small, fast-moving star that remains farther away. But even modest encounters can accumulate over time. Imagine an object at 50,000 astronomical units from the Sun. Its orbit is extremely elongated. Its gravitational binding energy is small. A passing star at a distance of 1 light year may slightly alter its velocity, perhaps changing it by a fraction of a meter per second. That sounds negligible, but at such weak binding it can be enough to reshape the orbit significantly. In some cases, the object's closest approach to the Sun may be lowered, sending it inward as a long-period comet. In other cases, the object may gain enough energy to become unbound entirely, drifting into interstellar space. This is how the outer Oort cloud slowly erodes, not in a catastrophic event, not in a dramatic collision, but through countless small gravitational nudges accumulated over billions of years. One of the most well-known examples of a past or future stellar encounter involves a star called Gliese 710. Astronomical calculations suggest that in about 1.3 million years, Gliese 710 will pass relatively close to the Sun, perhaps within 0.2 to 0.3 light years. That is far beyond the orbit of Neptune. It is even beyond the Kuiper Belt. But it lies well within the estimated outer boundary of the Oort cloud. When this encounter occurs, it is expected to disturb a significant number of Oort cloud objects. Over the following millions of years, the rate of long-period comets entering the inner solar system may increase. This will not threaten the planets directly in any immediate way. The probability of a comet striking Earth remains low, but statistically the flux of comets will rise. Gliese 710 is only one example. There have been many such encounters in the past, and there will be many more in the future. Some may have been closer than the upcoming pass of Gliese 710. Others may have involved more massive stars producing stronger perturbations. In the early solar system, stellar encounters were likely even more common. The Sun is thought to have formed within a dense stellar cluster, where stars were packed much more closely together than they are now. In that environment, close passes would have been frequent. These early encounters may have played a major role in shaping the Oort Cloud's initial structure. They could have helped to lift scattered Planier simals out of the flat plane of the early solar system and redistribute them into a spherical configuration. They may have stripped away some loosely bound objects before the Oort Cloud fully formed. In this sense, passing stars were not just destructive agents. They were architects. They helped transform a flattened disk of scattered debris into a three-dimensional halo. Once the Sun left its birth cluster and entered a quieter galactic neighbourhood, the rate of close encounters decreased. The outer Oort Cloud stabilised somewhat, though it remained vulnerable. The cumulative effect of these stellar encounters over billions of years is profound. Without them, the outer Oort Cloud might look very different. It might be more disk-like, retaining more of its original alignment with the planetary plane. The nearly isotropic distribution of long-period comets suggests that stellar perturbations have been significant. Another important aspect of stellar encounters is asymmetry. When a star passes near the Sun, its gravitational influence is not evenly distributed across the Oort Cloud. Objects on the side facing the passing star experience a stronger pull than those on the opposite side. This differential effect can stretch and distort the cloud temporarily. Over time, repeated encounters from different directions randomize these distortions, reinforcing the spherical shape. The orientation and velocity of the passing star also matter. A slow-moving star exerts a longer-lasting gravitational influence than a fast-moving one. Even if the closest approach distance is the same, a slower encounter can produce larger orbital changes. Mass plays a role as well. A red dwarf passing at 1 light-year may produce modest perturbations. A more massive star passing at the same distance could produce stronger effects. Fortunately, massive stars are less common in the galaxy, reducing the likelihood of extreme disruptions. Beyond individual stars, there are also larger-scale disturbances. The Sun's orbit around the Milky Way takes it through different galactic environments. It passes through spiral arms, regions with higher stellar densities and molecular clouds. These regions increase the likelihood of close encounters. Some researchers have proposed that periodic increases in comet activity in the inner solar system could be linked to the Sun's motion through such dense regions. While this idea remains debated, it highlights the connection between galactic motion and comet flux. Molecular clouds, in particular, can exert gravitational influence. These vast accumulations of gas and dust are far more massive than individual stars. If the Sun were to pass near or through a molecular cloud, the gravitational perturbations on the outer Oort Cloud could be significant. Such events are rare, but over billions of years not impossible. All of these disturbances share a common feature. They operate slowly and subtly. There is no visible shaking of the solar system. The planets do not wobble dramatically. The inner solar system remains largely unaffected. Only the outermost region, the loosely bound halo of icy bodies, responds, and even then the response unfolds over millions of years. From the perspective of Earth, the result is an occasional long-period comet, arriving unexpectedly from a random direction, glowing briefly in the sky before departing again for tens of thousands or millions of years. Each such comet is evidence of a distant disturbance. It is a messenger not only from the Oort Cloud, but from the Sun's galactic environment. Another intriguing possibility involves close stellar passages that may have already occurred but left subtle traces. Some unusual objects in the outer solar system, such as Sedna, and similar bodies with highly elongated and detached orbits, may bear the imprint of an early stellar encounter. Their orbits are difficult to explain through interactions with the known planets alone. If a star passed relatively close during the Sun's early history, it could have reshaped the outer regions and left behind a population of objects with distinctive orbital characteristics. Studying these objects provides indirect evidence of ancient stellar encounters. In this way, the Oort Cloud serves as a historical record. Its structure encodes information about the Sun's past interactions with neighbouring stars. Each perturbation leaves a subtle mark on the distribution of orbits. Over billions of years, these marks overlap and blend, but patterns remain. The fact that the Oort Cloud still exists at all suggests that most stellar encounters have not been catastrophic. They have been gentle enough to reshape rather than destroy. But that balance is delicate. If a star were to pass extremely close, within a fraction of a light year, the outer Oort Cloud could be severely disrupted. A significant fraction of its objects could be stripped away in a relatively short time. Such close encounters are rare in the Sun's current environment, but not impossible over cosmic timescales. This brings us back to the idea of the solar system as an open system. The outer Oort Cloud is not sealed off. It is exposed to the galaxy. Passing stars and galactic tides continually influence it. The Sun does not hold its distant companions in isolation. It holds them in a dynamic, interactive gravitational landscape. Understanding this landscape helps explain why the Oort Cloud is so vast yet so fragile. It exists at the threshold where stellar systems meet. If passing stars and galactic forces shape the Oort Cloud so profoundly, could other stars have similar structures? Do most stars possess their own distant clouds of icy debris? And if so, how common are these extended gravitational halos throughout the galaxy? Occasionally, without warning, something ancient enters the inner solar system and briefly steals the sky. It arrives from a direction with no obvious connection to the planetary plane, brightens as it approaches the Sun, grows a tail that can stretch for millions of kilometres, and then fades again, often never to return. These visitors are comets, and for our purposes they are far more than beautiful curiosities. They are evidence. Everything we think we know about the Oort Cloud rests, in one way or another, on the behaviour of comets. Without them, the idea of a vast, distant reservoir of icy bodies would be little more than speculation. With them, it becomes difficult to argue that such a reservoir does not exist. To understand why, it helps to look closely at what comets are and what makes long-period comets so unusual. A comet is essentially a frozen remnant from the early solar system. Its nucleus is a compact mixture of water ice, carbon dioxide ice, carbon monoxide ice, ammonia, methane, and rocky dust. These materials condensed in the cold outer regions when the planets were forming, billions of years ago. For most of their existence, comets remain inert, locked in darkness at temperatures only a few degrees above absolute zero. Nothing about them is active or dramatic until they approach the Sun. As a comet moves inward, solar radiation begins to heat its surface. Ices that have remained solid for billions of years start to sublimate directly into gas. This gas carries dust with it, forming a glowing envelope called a coma around the nucleus. Solar radiation pressure and the solar wind then push this material outward, creating the familiar tails. The spectacle we see is temporary. Once the comet moves away from the Sun, activity fades, the gas disperses, the dust spreads out. What remains is the same small, dark nucleus continuing along its orbit. Short-period comets, those that return every few years or decades, mostly originate in the Kuiper Belt. Their orbits are relatively well understood. They tend to lie near the plane of the planets. They return again and again until they exhaust their volatile material or are ejected. Long-period comets are different. Their orbital periods range from tens of thousands to millions of years. Many are observed making what appears to be their first and only visit to the inner solar system. Their orbits are highly elongated, and their inclinations are randomly distributed. One may plunge inward from far above the plane of the planets, another may arrive from far below. There is no preferred direction. This randomness is the key. If all comets originated in a flat disk like the Kuiper Belt, we would expect their orbits to cluster near that plane. That is exactly what we see with short-period comets. The long-period ones refuse to follow that pattern. Instead, they behave as though they are being drawn from a spherical source surrounding the Sun. That source, by necessity, must lie far away. The energies of long-period comets tell the same story. When astronomers calculate their original orbits, accounting for planetary perturbations, many of these comets appear to have started their journey at distances of tens of thousands of astronomical units. Some are so weakly bound that even small uncertainties in their velocity determine whether they are technically bound to the Sun or already on an escape trajectory. This is not what you would expect if their source were nearby. The Oort Cloud was proposed specifically to explain these observations. It provides a natural explanation for both the isotropic distribution of long-period comet orbits and their extreme energies. In this context, comets are not random debris. They are messengers from the deep freeze, carrying information from regions we cannot observe directly. Each long-period comet that enters the inner solar system is like a probe launched unintentionally, delivering a brief data packet before vanishing again into the dark. The rate at which these messengers arrive is also informative. On average, a few new long-period comets are discovered each year. Some are faint and go unnoticed. Others become spectacular, visible even to the naked eye. When astronomers correct for observational bias, they can estimate how many such comets likely enter the inner solar system annually. From that rate, they can infer how large the distant reservoir must be to sustain it over billions of years. The conclusion is unavoidable. The source must be enormous. If the Oort Cloud contained only a few million objects, it would have been depleted long ago. The steady trickle of long-period comets we observe today implies a population in the hundreds of billions or trillions. This inference is one of the strongest arguments for the Oort Cloud's existence. There is also a chemical dimension to this story. When comets are observed up close, either through telescopes or spacecraft missions, their composition reveals information about the conditions in which they formed. Many contain volatile compounds that would not survive repeated heating near the Sun. Their presence suggests that these objects have spent most of their existence far from solar warmth. Some long-period comets appear chemically pristine, showing fewer signs of processing than short-period comets that have made many close passes. This supports the idea that they have been stored in deep cold for billions of years. The Oort Cloud provides exactly such a storage environment. Another clue comes from the distribution of comet energies. Astronomers notice a clustering of long-period comet energies near zero. This suggests that many are arriving from a region where they were only barely bound to the Sun. That is consistent with an origin near the outer edge of the Sun's gravitational sphere of influence. If comets were coming primarily from closer regions, their energies would be more strongly negative. The observed distribution points outward, not inward. There is also a population known as dynamically new comets. These are comets whose orbits suggest they have never passed close to the Sun before. They are pristine arrivals entering the inner solar system for the first time. Their existence implies a vast reservoir that has remained largely untouched. Once a comet enters the inner solar system, its fate is uncertain. Some are ejected entirely after one pass, flung out by interactions with the giant planets. Others are captured into shorter period orbits. Many gradually disintegrate. This means that the Oort Cloud is not only a source but also a sink. Objects are constantly being removed from it, and yet the cloud persists. This persistence is another argument for its immense size. Now consider the timing. Long-period comets do not arrive in neat intervals. Their appearances are irregular. There may be years with several notable comets, followed by long quiet periods. This randomness reflects the chaotic nature of the perturbations that send them inward. Passing stars, galactic tides, and the combined gravitational effects of the planets all play roles. A small change in an object's orbit far out in the cloud can take millions of years to translate into an inward plunge. This means the comets we see today may have been disturbed long before humans existed. In some cases, the perturbation that set a comet on its current path may have occurred tens of millions of years ago. Perhaps during a close stellar encounter the Sun has long since left behind. So when a comet suddenly appears in our sky, it is not a spontaneous event. It is the delayed consequence of ancient gravitational interactions. This time lag adds another layer to their role as messengers. They're carrying information not only from distant space, but from deep time. Another intriguing aspect involves comet showers. Models suggest that particularly close stellar encounters can trigger bursts of comet activity, sending many objects inward over extended periods. These events, called comet showers, may last millions of years. Some researchers have explored whether such showers could be linked to mass extinction events on Earth, though this remains controversial. The evidence is not conclusive, and many extinctions are better explained by other mechanisms. Still, the possibility underscores the influence of distant gravitational disturbances on the inner solar system. The Oort Cloud is not isolated. Its behaviour can have consequences far closer to home. Comets also provide constraints on the cloud's shape. The nearly uniform distribution of long-period comet inclinations suggests that the outer Oort Cloud is close to spherical. Any significant flattening would leave a detectable signature in the arrival directions. This spherical symmetry is difficult to produce without the combined effects of stellar encounters and galactic tides acting over long periods. It reinforces the idea that the cloud has been shaped by its environment, not just by the Sun alone. Short-period comets, by contrast, tell us about the Kuiper Belt. Their different behaviour helps distinguish the two populations. Together, these comet populations form a kind of diagnostic tool. By studying their orbits, energies, and compositions, astronomers can piece together the structure of regions that cannot be observed directly. It is worth emphasizing how indirect this process is. No one has ever pointed a telescope at the Oort Cloud and seen it. No spacecraft has ever entered it. Everything we believe about it comes from these fleeting visitors and from the laws of gravity applied consistently. This makes comets uniquely valuable. They are not just debris, they are data. Another important detail is that not all long-period comets necessarily originate from the outermost regions. Some may come from the inner Oort Cloud, where objects are more tightly bound. These comets tend to have slightly different energy distributions. This distinction supports the idea of a layered cloud. The inner cloud supplies the outer cloud. The outer cloud supplies the comets. Over time, this flow maintains the population we observe. This layered structure also helps explain why the comet flux has remained relatively steady over billions of years, despite ongoing losses. Now think about visibility. Most long-period comets are faint. Only a small fraction become bright enough to attract public attention. Many pass through the inner solar system unnoticed, detected only by automated surveys or not at all. This means that the visible comets represent only the tip of the iceberg. For every bright comet that makes headlines, there may be dozens or hundreds that go unseen. Each one still represents a perturbation in the distant cloud. In that sense, the Oort Cloud is far more active than it appears. Its influence is continuous, even if our awareness of it is sporadic. Comets also remind us of scale in a more visceral way. A long-period comet's journey inward may take millions of years. Its visible phase may last months. Then it disappears again for eons. This ratio of visibility to invisibility mirrors the Oort Cloud itself. Vast, persistent, mostly unseen, revealing itself only briefly and indirectly. When you put all of this together, comets cease to be curiosities. They become the strongest evidence we have that the solar system extends far beyond the planets, beyond the Kuiper Belt, and deep into a distant, cold halo. They are the reason the Oort Cloud is taken seriously rather than dismissed as speculation. They are the reason astronomers can talk about distances of tens of thousands of astronomical units with confidence rather than hesitation. And they are the reason the Oort Cloud feels less abstract and more real, even though it remains invisible. If comets are messages from the deep freeze, what exactly are they telling us about where they come from? And more broadly, is the Oort Cloud truly something that belongs only to the Sun, or is it part of a larger pattern, repeated around other stars throughout the galaxy? Ownership sounds simple when we talk about planets. Earth orbits the Sun. Jupiter orbits the Sun. Their gravitational relationship is obvious, stable, and long-term. But once we move outward into the distant halo of icy bodies, the idea of ownership becomes less straightforward. The Oort Cloud challenges the assumption that the solar system is a neatly contained structure, belonging exclusively to one star. To explore whether the Oort Cloud is truly ours, we first need to clarify what belonging means in a gravitational sense. In astronomy, an object belongs to a star if it is gravitationally bound to that star. In simple terms, its total orbital energy relative to the star is negative. That means it does not have enough speed to escape permanently. It may wander far away, but gravity will eventually pull it back. By that definition, most objects in the Oort Cloud are part of the solar system. They orbit the Sun, even if those orbits take millions of years to complete. However, the strength of that binding varies enormously. A planet like Earth is deeply bound. To remove Earth from the Sun's gravitational influence would require a massive energy input. The same is true for Jupiter or Saturn. Even Neptune, far from the Sun compared to the inner planets, is securely anchored. An object at 50,000 astronomical units is different. It is bound, but weakly. A small change in velocity, perhaps delivered by a passing star or galactic tide, could be enough to unbind it completely. This weak binding means that Oort Cloud membership can be temporary on cosmic timescales. An object might remain bound for hundreds of millions of years and then be lost during a stellar encounter. Another object might drift into the Sun's gravitational sphere of influence and become bound after previously wandering freely through interstellar space. So if ownership is defined strictly by current gravitational binding, then yes, the Oort Cloud is ours, but only provisionally. Another angle on this question involves origin. Did every object in the Oort Cloud form within the solar system? The prevailing theory suggests that most did. During the early stages of planetary formation, countless icy planetesimals were scattered outward by interactions with the giant planets. Many were ejected entirely. Others were placed on elongated orbits that eventually evolved into the Oort Cloud. These objects would indeed be native solar system material, remnants of the same primordial disk that formed the planets. But that is not the whole story. The Sun was not born in isolation. It likely formed within a cluster of stars, perhaps containing hundreds or thousands of stellar siblings. In such an environment, close encounters would have been common. During those early interactions, material could have been exchanged. Computer simulations show that it is possible for stars in a cluster to capture planetesimals from one another, especially if relative velocities are low. This means that some fraction of the Oort Cloud may consist of objects that formed around other stars. If that is true, then part of what we call the Oort Cloud may not have originated here at all. More recently, we have direct evidence that interstellar objects exist. The discovery of Oumuamua in 2017 and comet Borisov in 2019 confirmed that small bodies can travel between star systems. These objects pass through the inner solar system on hyperbolic trajectories, clearly unbound to the Sun. Most interstellar visitors likely pass through unnoticed, especially if they never come close to the Sun. Under the right conditions, however, capture is theoretically possible. If an interstellar object passes near the Sun at a low relative speed and experiences a gravitational interaction with one of the giant planets, it could lose enough energy to become bound. If captured into a distant elongated orbit, it might join the Oort Cloud. Such captures are expected to be rare, but over billions of years, rare events accumulate. This possibility complicates the idea of ownership further. If some Oort Cloud objects originated elsewhere, and if some originally solar system objects have been lost to other stars, then the Oort Cloud becomes less a private domain and more a shared reservoir within the galaxy. The boundary between solar system material and interstellar material becomes porous. Another consideration involves overlapping gravitational spheres of influence. As discussed earlier, the Sun's gravitational sphere extends perhaps 1 to 2 light-years. The nearest star systems have their own spheres of influence. In some regions of space, especially within stellar clusters, these spheres can overlap significantly. During close stellar encounters, objects in the outer Oort cloud may temporarily experience comparable gravitational forces from both stars. Some may be transferred from one star's cloud to another. This exchange mechanism suggests that Oort-like clouds around different stars are not entirely isolated. They may interact, especially in the early stages of stellar evolution, when stars are closer together. This leads to a broader question. Is the Oort cloud unique to the Sun? The processes that formed it, planet formation, gravitational scattering by giant planets, stellar encounters, are not unique. Observations of exoplanetary systems reveal that giant planets are common, stellar clusters are common, galactic tides affect all stars orbiting within the Milky Way. Given these similarities, it would be surprising if the Sun were the only star with a distant halo of icy bodies. While we cannot observe Oort clouds around other stars directly, theoretical models suggest that they should be widespread. Many stars with planetary systems likely possess their own distant reservoirs of icy debris. If that is true, then the Oort cloud is not a rare anomaly. It is a typical byproduct of planetary system formation. That realization changes the emotional framing of the question. Instead of asking whether the Oort cloud truly belongs to us, we might ask whether any Oort cloud truly belongs to any star. These structures may be common features of stellar systems, shaped by local dynamics, but influenced by the shared galactic environment. Ownership in this context becomes relative rather than absolute. There's also a temporal dimension to consider. Right now, most Oort cloud objects are bound to the Sun. In the distant future, that may not be true. As the Sun continues its orbit around the Milky Way, it will encounter new stellar neighbours. Over billions more years, it will likely lose additional outer cloud objects. Some may be captured by other stars. Others may drift freely in interstellar space. Eventually, when the Sun exhausts its nuclear fuel and evolves into a red giant and then a white dwarf, the gravitational environment of the solar system will change. Mass loss during the red giant phase will weaken the Sun's gravitational hold, causing planetary orbits to expand and potentially unbinding some distant objects. The outer Oort cloud, already tenuous, could be significantly depleted during this phase. In that far future, the idea that the Oort cloud belongs to the Sun may no longer apply in any meaningful sense. This long-term perspective reinforces the idea that gravitational ownership is always conditional. On timescales of human civilization, the Oort cloud is part of the solar system. On timescales of galactic evolution, it is a transient structure. Another interesting aspect involves the philosophical meaning of hours. When we speak of the solar system, we often include everything gravitationally bound to the Sun. By that definition, the Oort cloud is ours as much as Neptune is. But the psychological distance is enormous. Neptune can be imaged clearly. Its orbit is well measured. Spacecraft have visited it indirectly through flybys of its moon Triton. The Oort cloud remains invisible and unreachable with current technology. Even our fastest spacecraft have barely begun to leave the heliosphere, the bubble carved by the solar wind, which itself lies far inside the Oort cloud's inner boundary. Voyager 1, after decades of travel, has reached a distance of roughly 160 astronomical units. That is still less than 10% of the distance to the inner Oort cloud. So while the Oort cloud is technically part of the solar system, it remains practically inaccessible. This practical inaccessibility makes it feel less like ours, even though gravitationally it is. There is also the question of influence. the planets influence one another significantly. Jupiter shapes asteroid orbits, Saturn affects comet trajectories, Neptune sculpts the Kuiper Belt. The Oort Cloud, by contrast, exerts almost no influence on the inner solar system except through rare comet arrivals. It is part of the system, but it is not central to its daily dynamics. This marginal role reinforces the sense that it is peripheral, an outer archive rather than an active participant. Yet in terms of sheer size, it dominates. If we define the solar system by its gravitational reach, then the Oort Cloud represents the majority of its physical extent. The planets occupy a tiny inner fraction, so in terms of space, the Oort Cloud is more representative of the solar system's size than the planetary region. This contrast between physical extent and practical significance adds another layer to the ownership question. In one sense, the Oort Cloud is the solar system's outermost domain. In another, it is a loosely connected appendage, constantly influenced by the galaxy. Perhaps the most accurate answer is that the Oort Cloud is both ours and not entirely ours. It is ours in that it formed largely from solar system material, is currently bound to the Sun, and defines much of the Sun's gravitational territory. It is not entirely ours in that its outermost members are weakly bound, subject to galactic forces, and potentially exchanged with other stars over time. It sits at the interface between the Sun and the galaxy. That interface is not a wall, it is a gradient. Step outside the Sun's most distant companions, and the environment changes in a way that is subtle rather than dramatic. There is no gate, no sudden emptiness, no sign announcing that one domain has ended and another has begun. Instead, the solar system gradually blends into something larger, quieter, and far less personal. This is the interstellar neighbourhood, the region of space where the Sun is no longer the primary reference point, and where the galaxy itself becomes the dominant presence. To understand what lies beyond the Oort Cloud, it helps to release the idea that interstellar space is a void. It is not empty in any meaningful sense. It is thin, yes, but it is structured. It contains gas, dust, magnetic fields, cosmic rays, and the faint gravitational influence of countless stars moving along their own trajectories. The transition from the Oort Cloud into this broader environment is not marked by distance alone. It is defined by influence. Inside the Oort Cloud, even at its most distant edges, the Sun still matters. Its gravity may be weak, but it remains the single most important force acting on bound objects. Beyond that region, the balance shifts. The Sun becomes just one gravitational contributor among many. At that point, an object's motion is shaped more by the collective mass of the Milky Way than by the star it once orbited. The interstellar neighbourhood begins, loosely speaking, where the probability of long-term solar binding drops sharply. Objects passing through this region are no longer reliably captured by the Sun, nor are they guaranteed to remain associated with it if they are temporarily bound. Their trajectories are shaped by galactic tides, nearby stars, and the overall gravitational landscape of the galaxy. This region is not static, it is dynamic on vast timescales. The Sun itself is moving through it. Right now, the Sun is travelling through a region known as the local interstellar cloud, sometimes called the local fluff. This is a slightly denser patch of interstellar gas embedded within a much larger lower density cavity called the local bubble. The local bubble is thought to have been carved out by ancient supernova explosions, leaving behind a region of hot, diffuse gas. Within this environment, the density of matter is extremely low by terrestrial standards, but not negligible. There are a few atoms per cubic centimetre, mostly hydrogen and helium, along with trace amounts of heavier elements. There is also dust, microscopic grains drifting slowly through space. The Sun ploughs through this material as it orbits the galaxy, and its motion shapes the heliosphere, the bubble carved out by the solar wind. The heliosphere marks a magnetic boundary, not a gravitational one, and it lies far inside the Oort Cloud. Beyond the heliopause, where the solar wind gives way to interstellar plasma, the sun's magnetic influence fades, but gravity continues much farther. Still, once you move beyond the outer Oort cloud, gravity alone is no longer enough to define a system. Objects in the interstellar neighbourhood are influenced by the combined mass of billions of stars, as well as dark matter, which makes up a significant fraction of the galaxy's mass. This background gravitational field sets the baseline motion for everything in the Milky Way. In this environment, stars are not isolated islands. They are participants in a shared dynamical system. Each star carries with it a small region where its gravity dominates, but those regions overlap and interact. The farther you move from any given star, the more its influence blends into the galactic background. This blending is why the concept of between stars is misleading. There is no sharp boundary where one star's domain ends and another's begins. There are only regions where one influence outweighs another. The interstellar neighbourhood is where those weights become comparable. Another important feature of this region is relative motion. Stars do not sit still with respect to one another. They move at different speeds and in different directions around the galactic centre. Some move faster, some slower. Some oscillate above and below the galactic plane. Over time, these motions cause stars to drift past one another. From the sun's perspective, nearby stars appear to approach and recede over millions of years. Today's neighbours were not yesterday's neighbours, and they will not be tomorrow's. This constant reshuffling means that the interstellar neighbourhood is ever changing. The sun's nearest stellar neighbour at any given moment is not fixed. Over the sun's lifetime, many stars have passed closer than Alpha Centauri is today. Some will do so in the future. Each close pass slightly reshapes the gravitational environment of the outer solar system. This is why the Oort cloud and the interstellar neighbourhood cannot be treated as separate realms. They are coupled. The outermost Oort cloud exists within the interstellar neighbourhood. It is shaped by it. It responds to it. Beyond the Oort cloud, objects do not orbit the Sun in any meaningful sense. Instead, they follow paths determined primarily by the galaxy. Some of these objects are free-floating, never bound to any star. Others may have been ejected from planetary systems long ago. Some may have formed in isolation within collapsing gas clouds. We know such objects exist because we have detected them indirectly. Gravitational microlensing surveys suggest that there may be enormous numbers of free-floating planets in the Milky Way, perhaps even more than there are stars. These objects wander through interstellar space without a parent star, shaped only by the galaxy's gravitational field. In addition to rogue planets, there are countless smaller bodies, asteroids, comet-like objects, dust grains, and gas clouds. Occasionally, some of these wanderers pass through the solar system. The discovery of Oumuamua in 2017 was the first confirmed detection of an interstellar object passing through our neighbourhood. Its trajectory was hyperbolic, meaning it was not bound to the Sun. It came from outside the solar system and left again, never to return. 2 years later, comet Borisov was detected on a similar path. Unlike Oumuamua, it displayed classic cometary activity, confirming that icy bodies can travel between stars. These discoveries were not surprises in a theoretical sense, they were expected. What surprised astronomers was how detectable they were, suggesting that interstellar objects may be more common than previously thought. If that is the case, then the interstellar neighbourhood is not empty of solid bodies. It is populated quietly by debris from countless star systems. This population overlaps spatially with the outermost regions of the Oort cloud. From a gravitational perspective, the distinction between a loosely bound Oort cloud object and a passing interstellar object can be thin. The difference may come down to a small change in velocity. An object moving slightly slower relative to the Sun may become temporarily bound. One moving slightly faster will pass through and leave. This sensitivity reinforces the idea that the outer boundary of the solar system is not a line but a zone of exchange. Another defining feature of the interstellar neighbourhood is timescale. Motion here is slow. Not slow in an absolute sense, but slow relative to human perception. A star passing within a light year of the Sun may take tens of thousands of years to approach and tens of thousands more to recede. The gravitational influence builds gradually and fades gradually. For objects in the outer Oort Cloud, this slow change is significant. Their weak binding allows these gradual forces to accumulate, altering orbits without dramatic events. In the deeper interstellar neighbourhood, objects are not bound long enough for such slow accumulation to matter in the same way. Their paths are governed by broader galactic dynamics. The galaxy itself rotates. Stars orbit the galactic centre on timescales of hundreds of millions of years. Superimposed on that motion are smaller oscillations, epicycles and vertical movements through the galactic plane. The Sun participates in all of these motions. As it moves, the environment around it changes. Gas density varies, stellar density varies, gravitational perturbations vary. This means the interstellar neighbourhood is not uniform. There are quieter regions and busier ones, regions with few nearby stars and regions with many, regions dominated by diffuse gas and regions influenced by molecular clouds. Over the Sun's lifetime, it has passed through several such environments and will pass through many more. Each passage subtly affects the outskirts of the solar system. This dynamic context helps explain why the Oort Cloud looks the way it does today. It is not merely a product of early solar system formation. It is the result of billions of years of interaction with the interstellar neighbourhood. In that sense, the Oort Cloud is as much a galactic structure as a solar one. Beyond it, the interstellar neighbourhood continues without regard for any single star. Distances between stars average several light years, but those distances are not empty corridors. They are filled with the collective influence of the galaxy. Light travels through this region carrying information from distant stars. Cosmic rays propagate through it, shaped by magnetic fields. Dust grains drift slowly, sometimes accumulating, sometimes dispersing. Occasionally, shock waves from supernovae sweep through, compressing gas and triggering new star formation elsewhere. The solar system is embedded in this environment, not isolated from it. The interstellar neighbourhood also provides context for how we think about scale and belonging. From Earth, the Sun feels like the centre of everything. From the perspective of the galaxy, it is one star among hundreds of billions, moving along a prescribed orbit shaped by the galaxy's mass distribution. The Oort Cloud marks the region where that broader perspective begins to matter more than the local one. Beyond it, the Sun's identity fades into the background of the Milky Way. This does not mean the solar system becomes insignificant. It means it becomes one participant in a much larger system. Understanding this helps avoid a common misconception. When people imagine leaving the solar system, they often picture a dramatic exit, a moment when everything familiar falls away and something fundamentally different begins. In reality, the transition is gentle. The interstellar neighbourhood begins quietly. The Sun does not abruptly lose its influence. It gradually shares it. The Oort Cloud does not suddenly stop. It thins, frays, and blends. This blending is a defining characteristic of gravitational systems on large scales. Another implication of this blending is that the galaxy may be filled with overlapping halos. If most stars have Oort-like clouds, then the interstellar neighbourhood may be threaded with countless overlapping regions of weak gravitational influence. These halos may intersect, exchange material, and reshape one another over time. In dense stellar environments such as star clusters or the galactic centre, these interactions would be even more frequent. In quieter regions like the Sun's current location, they occur more slowly, but they still occur. This picture transforms how we think about the structure of the galaxy. Rather than a collection of isolated stars with neat boundaries, the Milky Way becomes a web of overlapping gravitational domains, constantly interacting at their fringes. The Oort Cloud is our local expression of that web. Beyond it lies not emptiness, but continuity. Stand back for a moment and picture the entire structure at once. Not just the planets, not just the Kuiper Belt, not even just the distant halo of icy bodies we've been slowly mapping in our minds. Picture the Sun as a small gravitational centre embedded inside a sphere that stretches nearly halfway to the nearest star, a sphere so vast that the region we usually call the solar system occupies only a tiny inner fraction of it. That is the scale we have been unfolding. We began close to home, where distances can still be expressed in astronomical units without discomfort. We moved past Neptune, through the Kuiper Belt, across the scattered disk, and outward into a region where numbers expanded rapidly. We watched the inner Oort Cloud emerge as a hidden reservoir, more tightly bound and quietly maintaining balance. We followed the outer Oort Cloud outward to its tenuous boundary, where the Sun's gravitational authority begins to fade into the broader influence of the Milky Way. Now, at this edge, the concept of an ending feels less appropriate than the concept of drifting. The outer Oort Cloud does not form a wall, it forms a gradient. Objects become fewer, binding becomes weaker, external influences grow stronger. Eventually, the distinction between solar and interstellar becomes a matter of probability rather than certainty. This is the solar system's outermost posture, not rigid, not sharply defined, but gently dissolving into its surroundings. The phrase edge of forever sounds dramatic, but the reality is quieter than that. There is no dramatic drop-off into nothingness. There is only a shift in dominance, a slow handoff from one gravitational authority to another. Inside this enormous sphere, icy bodies orbit so slowly that a single revolution may take millions of years. Their temperatures remain near absolute zero. Sunlight reaches them faintly, and then fades into the general starlight of the galaxy. Most of these objects will never be seen. Most will never enter the inner solar system. They will simply continue their silent paths, shaped by forces too gradual to notice on short timescales. And yet, occasionally, one is nudged. A passing star shifts its orbit slightly. The galaxy's tidal field stretches it just enough. Its closest approach to the Sun drops. Over thousands or millions of years it falls inward. It becomes visible. It grows a tail. It arcs across our sky for a few months and then disappears again. That brief appearance is the only sign that the vast halo exists. Without those comets, the Oort Cloud would remain entirely theoretical. With them, it becomes difficult to deny that the Sun's reach extends far beyond the region of planets. This leads to a perspective shift. If someone asks how big the solar system is, the honest answer depends on what you include. If you mean the region of major planets, it fits comfortably within a few dozen astronomical units. If you mean the Kuiper Belt, it stretches to perhaps 50. If you include the scattered disk, you move into the hundreds. But if you define the solar system as everything gravitationally bound to the Sun, then the answer grows to tens of thousands of astronomical units, perhaps more than a light year in radius. That is a difference of 3 orders of magnitude. On that larger scale, the planets are not the defining feature of the solar system, they are its dense inner core. The Oort Cloud is what sets its true spatial extent. This realization can feel disorienting. We are accustomed to thinking of the solar system as something compact and tidy. A central star, a series of orbiting planets, perhaps a belt of asteroids and icy debris beyond. That picture is not wrong, but it is incomplete. The fuller picture is more diffuse. It includes a spherical halo that merges gradually into the galaxy. It includes objects that may not have formed here. It includes bodies that will not remain here forever. It includes exchange. Over billions of years, the Sun has likely lost some of its distant objects to interstellar space. It may have captured others. The Oort Cloud may contain material that once orbited another star. Other stars may host fragments that once belonged to the Sun. In that sense, drifting at the edge of forever is not just a poetic phrase. It is a physical description. The outermost objects are not firmly anchored. They drift in weak gravitational currents. They reside in a region where belonging is temporary and influence is shared. This drifting also has a temporal dimension. The Sun itself will not last forever in its current state. In roughly 5 billion years, it will exhaust the hydrogen in its core and expand into a red giant. During that process, it will lose mass, its gravitational grip will weaken, planetary orbits will expand. Some objects currently bound may become unbound. The outer Oort Cloud, already fragile, will likely shed a significant fraction of its population. After the Sun becomes a white dwarf, its gravitational sphere of influence will be smaller. The Oort Cloud, as we know it today, will not exist in the same form. This future reminds us that even large-scale structures are temporary. The Oort Cloud has likely been evolving since the earliest days of the solar system. It was shaped by the Sun's birth cluster, by early stellar encounters, by planetary migration. It has been eroded by passing stars and galactic tides. It will continue to change. So when we ask how big the Oort Cloud really is, the answer is not fixed. It depends on time as well as distance. Today, it may extend to 50,000 or 100,000 astronomical units. In the past, it may have been larger. In the future, it may be smaller. The edge drifts. This drifting does not make the Oort Cloud less real. It makes it more dynamic. It is not a frozen boundary drawn once and for all. It is a living interface between a star and its galaxy. There is something quietly humbling about that. The region that defines the true size of our solar system is one we cannot see directly. It is one we cannot visit with current technology. It is inferred from subtle clues and long-term statistical patterns. It exists mostly in darkness and extreme cold, and yet it shapes how we understand our place in the galaxy. Because if the solar system extends nearly halfway to the nearest star, then we are not living in a small, isolated bubble. We are embedded in a gravitational structure that brushes against others. Stars are not separated by empty voids. Their outer halos overlap. Their influences interact. The galaxy is not just a collection of points of light. It is a web of extended domains. The Oort Cloud is our local expression of that web. It marks the place where the Sun's influence fades, but does not abruptly end. It marks the region where galactic forces begin to matter as much as local ones. It marks the threshold between the familiar architecture of planets and the broader dynamics of the Milky Way. From Earth, none of this is visible. The night sky does not reveal the Oort Cloud as a glowing sphere. It does not outline the Sun's gravitational boundary. What we see are stars scattered across the darkness. But hidden within that darkness is a region of space that belongs loosely and temporarily to the Sun. When you think about the scale again, it becomes clear why the question, how big is the Oort Cloud, cannot be answered with a single number that satisfies intuition. It is as big as the Sun's gravitational patience allows. It is as big as the galaxy permits. It is as big as the delicate balance between binding and escape. And that balance is not static. The outermost objects are drifting, always. Some are drifting inward, becoming comets. Some are drifting outward, becoming interstellar wanderers. Some are simply circling slowly, unnoticed, for millions of years. In this way, the Oort Cloud is less a structure with edges and more a slow-motion flow. A flow of icy bodies between star and galaxy. A flow that has been ongoing since the solar system's earliest days. As you let that idea settle, the scale becomes less overwhelming and more continuous. The planets orbit. The Kuiper Belt persists. The inner Oort Cloud holds steady. The outer Oort Cloud thins. The galaxy exerts its influence. Stars pass. Objects drift. No abrupt endings, no sharp lines, just gradual transitions. And somewhere far beyond Neptune, far beyond the faint sunlight that reaches even the most distant icy body, the Sun's presence fades into the shared gravity of the Milky Way. Not with a boundary, but with a whisper that stretches outward until it becomes indistinguishable from the background hum of the galaxy itself and continues drifting there.